Between two dying galaxies, something impossible is being born. A black hole 1 million times the mass of our Sun has appeared. It appeared where no black hole should ever exist. It floats in the void between colliding worlds. It feeds on a glowing bridge of hydrogen gas. We thought black holes needed billions of years to grow this massive. We were completely and utterly wrong. The James Webb Space Telescope just found evidence of direct collapse. This is a cosmic shortcut that breaks every single rule. This new discovery changes everything we thought we knew. Two galaxies are tearing each other apart. Their death dance created something astronomers had never seen. Researchers Pieter van Dokkum and Gabriel Brammer were scanning images. They were looking through archived data from the Space Telescope. Suddenly they stopped their search completely cold. There, on their computer screens, sat a shape that should not exist anywhere in nature. It was a perfect and luminous figure 8. An infinity symbol was blazing in the cosmic dark. The powerful image shows two brilliant red galactic cores. Each core is wrapped in glowing rings of newborn stars. They mirror each other perfectly like cosmic twins. They seem frozen in a moment of cosmic time. Between them stretches a long bridge of bright green light. This is hydrogen gas, stripped down to its bare atomic bones. The object was named the Infinity Galaxy. Scientists confirmed how it formed in the distant past. Two massive spiral galaxies slammed into each other head-on. The collision was so violent, it reshaped everything. But something makes this discovery stranger than the shape. That green bridge of gas is glowing for a specific reason. Something in the very middle of it is eating it. Something was there that was not supposed to be. The two galaxies collided with an incredible amount of force. Their stars were flung outward into vast glowing rings. Their massive gas clouds smashed together in the center. Think of two water balloons hitting each other at high speed. The rubber of the balloons flies apart in all directions, but the water inside crashes together in a single explosive burst. That is precisely what happened here on a cosmic scale. Except the water is 1 trillion times the mass of our Sunday, and the incredible explosion is still happening today. The telescope's infrared camera can see through the cosmic dust. The dust hides these collisions from regular optical telescopes. The image reveals details that are invisible to human eyes. The twin galactic cores glow with a deep red color. They are packed with older, more evolved stars. The surrounding rings shine with young, hot blue stars. These stars were born from the chaos of the collision, and that bright green glow is the hydrogen gas. That is hydrogen being ripped apart by immense gravity. The team nicknamed the object the Infinity Galaxy. They named it because of its remarkable shape, but the new name now carries an extra weight of meaning. This collision might have created something that could exist forever. Something that can never be destroyed by any known force. It may have created a new supermassive black hole. Galaxy collisions happen all throughout the universe. They are not a particularly rare cosmic event, but this specific collision revealed a cosmic recipe, a recipe that scientists have been hunting for decades. The exact conditions needed to birth a true monster. Nobody expected to find what came next in the data. The team looked closer at that glowing green bridge. They found the signatures of intense radiation. X-rays and radio waves were pouring out of the center. These are the telltale signs of a supermassive black hole. A black hole that is actively feeding and growing. But supermassive black holes live at the centers of galaxies. They are the massive anchors around which everything else orbits. This one was found floating in the space between two galaxies. The discovery triggered an immediate and difficult puzzle. How did a black hole weighing 1 million solar masses end up there? How did it end up in the middle of absolute nowhere? Did it get ejected from one of the colliding galaxies? Did it simply wander in from somewhere else in the void, or did something far stranger happen in this location. The answer would force scientists to reconsider everything they thought they knew about how black holes form. But first, they had to prove this black hole was an anomaly. They had to prove it was not supposed to be where they found it. Black holes do not float around in empty space. They do not drift like cosmic tumbleweeds in the desert. They sit at the very hearts of their host galaxies. They are trapped there by gravity since the universe was young. Every major galaxy ever studied has one at its core. Our own Milky Way has Sagittarius A star. It is 4 million times the mass of our Sunday. The Andromeda Galaxy hosts one that is even bigger. They are the galactic anchors, not cosmic wanderers. So when the research team confirmed a supermassive black hole, a black hole sitting between the two cores of the Infinity Galaxy, the entire astronomy community erupted with difficult questions. This was not a small stellar black hole drifting through space. Those kinds of objects exist and are manageable mysteries. This was a true giant, a cosmic beast of immense size. A beast that should be locked in place by the gravity of billions of stars. The black hole sits exactly in the middle of the Green Bridge. It is not near one galaxy or the other, but dead center. It is like someone carefully and deliberately placed it there. The team measured its precise position dozens of times. Every single measurement confirmed the same impossible fact. 3 different possibilities emerged almost immediately. Maybe the black hole got ejected from one of the galaxies, ejected during the incredibly violent crash between them. Supermassive black holes can get kicked out of their homes. This can happen during violent galaxy mergers, but it is rare. Computer simulations show that when 2 galaxies merge, their central black holes will eventually spiral together. During that final death spiral, they can throw each other around. They can act like a pair of cosmic wrestlers in a ring. But these ejected black holes travel at extreme speeds. They race through the vastness of space at thousands of miles per second. They are fleeing their birthplace like giant cosmic bullets. If this black hole had been thrown out of a galaxy, it should be moving very fast relative to everything around it. The second possibility seemed even stranger than the first. Maybe a third hidden galaxy sits directly behind the Infinity Galaxy. A hidden galaxy from our particular perspective on Earth. A galaxy that just happens to line up perfectly with the collision zone. Its central black hole would then appear to sit between the 2 main galaxies, even though it is actually much farther away from them. This is a simple cosmic illusion caused by alignment. This kind of alignment happens sometimes in astronomy. It is known by the technical term of a chance superposition. It is like seeing 2 stars that appear right next to each other, but they are actually separated by trillions of miles. Perspective tricks are very common in the vastness of space. The third possibility made the researchers pause and think, what if the black hole did not come from anywhere else? What if it actually formed right there in that bridge of gas? What if it formed during the collision itself? This particular option violated everything in the textbooks. Black holes do not just spontaneously appear in clouds of gas. They need something massive to collapse to form them. Usually, this is a massive star at the end of its life. Stars live for millions or billions of years. Then they die in powerful supernova explosions. These explosions can leave black holes behind as remnants. That is the standard story of black hole formation. It is the only story that anyone had ever been able to prove. But there is another theory whispered about in research papers, a theory that suggests another way for black holes to form, a cosmic shortcut that bypasses the need for stars. Under perfect conditions, a massive cloud of gas could skip the star phase. It could collapse straight into a black hole directly. Scientists call this theoretical process direct collapse. They had never actually seen it happen in the universe. Until now, it had remained a purely theoretical idea. The team knew that they needed some definitive proof. They needed to measure how fast the black hole was moving. They needed to compare its motion to the gas around it. If it was racing through the gas at a high speed, that would strongly support the ejection theory. If it sat motionless, perfectly embedded in the gas cloud, like a patient spider sitting in the middle of its web, that would suggest something far more revolutionary had occurred. They applied for more time on the powerful space telescope. The long and anxious period of waiting then began. But while they waited, they started to calculate its mass. They wanted to know exactly how massive this mystery black hole really was. The numbers that they calculated would completely shock them. The black hole weighs as much as 1 million suns. All of that mass is crammed into a space smaller than our solar system. Let that incredible fact sink in for just a moment. 1 million stars like our own sun, all compressed into a region where gravity becomes so intense that nothing, not even light, can ever escape. The team calculated this mass using multiple different methods, and every single calculation that they performed pointed to the same number. To understand how absurd this is, you need to know how black holes grow. They normally start out very small after a star dies. A typical stellar black hole is born from a dying star. It weighs maybe 10 to 100 times the mass of the Sunday. That is the initial seed for a much larger black hole. From there, it grows by eating the material around it. Gas falls in and dust spirals down into its grasp. Maybe it will merge with another black hole during a galaxy collision. This entire process takes a very long time. It takes billions of years of slow and steady growth. Astronomers have a formula for how fast black holes can grow. This formula is called the Eddington limit. As material falls into a black hole, it heats up. It heats up and releases a tremendous amount of radiation. That radiation then pushes back against the infalling matter. It pushes back like a very strong and persistent wind. There is a maximum rate at which a black hole can feed. It cannot feed before its own light pressure stops more food from falling in toward it, even if it is feeding at that maximum rate constantly. A 10 solar mass black hole would need billions of years to reach a mass of 1 million solar masses. The universe is 13.8 billion years old. That gives plenty of time for black holes to bulk up. But here is the fundamental problem with that idea. The James Webb Space Telescope keeps finding supermassive black holes. It finds them in the very early history of the universe. Black holes with billions of solar masses are seen. They existed when the cosmos was less than 1 billion years old. Some of them appeared just 500 million years after the Big Bang. The math for their growth simply does not work out. There was not enough time for small stellar black holes to grow so massive, not even if they fed at the maximum possible rate non-stop. It is like finding a full-grown oak tree in a forest that was planted only yesterday. Something is very wrong with our story of black hole growth. The Infinity Galaxy's black hole weighs 1 million solar masses. It sits in a collision zone that formed relatively recently. The two galaxies first smashed together billions of years ago, but compared to the total age of the universe, this collision is recent. There is no nearby star that is dense enough to have died, and left behind a black hole that is this massive. This mass sits in a specific category that makes scientists uncomfortable. It is too big to have come from a single normal star. It is too small to be an ancient galaxy core black hole. It is exactly the size that direct collapse theory predicts. It predicts this size for a newborn supermassive black hole. When gas clouds collapse directly without forming stars first, the theory suggests they create black holes of a certain mass, between 100,000 and 1 million solar masses. These are called heavy seeds by scientists who study them. They are born big and they are born very fast. They are ready to grow into the giants we see powering ancient quasars. The team stared at their new mass calculations in disbelief. 1 million solar masses sitting in a gas cloud between galaxies. The number fit the direct collapse predictions perfectly. It was too perfect to be a simple coincidence. But the mass alone does not prove anything for certain. Plenty of black holes can reach 1 million solar masses through normal growth. What made this one so special was not just its weight, it was where that immense weight existed in space, and whether that weight was moving or if it was stationary. The velocity measurements for the object would arrive soon. Until then, the team turned their attention back to the gas, the glowing green gas that was surrounding this cosmic beast. That hydrogen glow held its own set of secrets, secrets that would confirm their wildest suspicions. The green light stretching between the galaxy cores is not just pretty, it is a cosmic crime scene photograph showing what is happening. It is showing us what is happening in real time. That glow comes from ionized hydrogen atoms, atoms that have been stripped of their electrons. They have been stripped by some intense source of radiation. Hydrogen in its normal state is completely invisible. It is invisible in the wavelengths that the telescope observes. But if you blast it with enough energy, it will light up. It will light up like a giant cosmic neon sign. Something in the middle of that gas bridge is pumping out energy. It is pumping out enormous amounts of pure energy. Something in the middle of that bridge is eating. And when black holes eat, they get very messy. Gas does not fall straight into a black hole. It does not fall like water going down a drain. It spirals inward, forming a disk around the black hole. This structure is called an accretion disk. Friction in that disk heats the gas to millions of degrees. That superheated gas then screams out radiation. It screams out radiation across the entire electromagnetic spectrum. Ultraviolet light X-rays and radio waves are all produced. That powerful radiation then slams into the surrounding hydrogen gas. It rips the electrons away from their host atoms. The atoms do not stay in this ionized state forever. Eventually, they will recapture some free electrons, and when they do, they release light at specific wavelengths. The telescope's camera detects that light as being green. It is green in the false color images that we see. The green glow maps out exactly where the black hole's radiation reaches. The team was able to measure the size of this ionized region. It extends across thousands of light years of space. A vast swath of the cosmos is being lit up by the feeding black hole. This is not a small or insignificant effect at all. This is industrial-scale cosmic violence happening. The black hole is actively accreting matter right now. It is pulling in gas from the surrounding cloud, and it is converting that matter into intense radiation. But here is what made the scientists lean forward. The ionized gas is not concentrated around either of the two galaxy cores. It is concentrated in the space that is between them. The brightest, most intense ionization sits right where the black hole lurks, like a bright spotlight shining on a dark stage. The green glow illuminates the exact location of the hidden monster. The team combined the new infrared data with other observations. The Chandra X-ray Observatory detected hard X-rays. They were coming from the very same location in space. X-rays are the smoking gun evidence of black hole accretion. Only black holes and neutron stars can produce X-rays with those energies, and neutron stars are far too small to generate this much power. The Very Large Array is a massive network of radio telescopes. It is located in the desert of New Mexico. It picked up powerful radio emissions from the same spot. Black holes are known to launch jets of particles. They launch them at nearly the speed of light when they feed. These powerful jets are known to emit radio waves. The radio signal confirmed that something with tremendous mass was there. Something with a huge amount of energy sat in that hydrogen bridge. 3 independent telescopes were observing in 3 different types of light. They were all pointing at the very same cosmic address. They were all seeing the signature of an actively feeding black hole. A supermassive black hole that was not near the galaxies. A black hole that was not hiding behind them. It was right in the middle where it had no business existing. The ionized hydrogen also revealed something else that was crucial. The team could measure how the gas was moving. Ionized atoms will emit light at very specific wavelengths, but if those atoms are moving toward or away from us, the wavelengths of the light they emit will shift slightly. This phenomenon is known as the Doppler effect. It is the same thing that makes an ambulance siren change pitch. It changes pitch as it drives past you on the street. By measuring these small wavelength shifts in the light, astronomers can determine how fast the gas is moving. They can also determine in what direction it is moving. The team analyzed the ionized hydrogen throughout the entire bridge. They found that it was swirling, turbulent, and chaotic. The collision between the two galaxies had stirred this gas. It had stirred it into a state of violent motion. Powerful shock waves were rippling through the entire region. The pressures and temperatures were fluctuating wildly. This level of chaos in the gas mattered a great deal. This turbulence would become central to their final argument. But first they needed to measure the black hole's velocity, and they needed to compare it to the velocity of the gas. That crucial measurement would arrive within just a few weeks. Until then, they documented every single detail of the green glow. Every nuance of the ionization pattern was recorded. The glow had proved that a black hole was there. The velocity would prove how it got there in the first place. The difference between those two facts would rewrite the textbooks. For many decades, scientists believed they understood black hole formation. The story of their formation seemed simple and very logical. Stars die, and then black holes are born from their remnants. And those black holes then grow slowly over cosmic time. This is known as the light seed theory of black hole growth. And until recently, nobody had seriously questioned it. The evidence for it seemed to be completely solid. Here is how this process is thought to work. The universe's very first stars formed about 200 million years ago. These were not stars that were like our own Sunday. They were true monsters, some weighing 100 to 300 times the sun's mass. They burned incredibly hot and also incredibly fast. They exhausted all of their nuclear fuel in just a few million years. When they finally died, they collapsed into black holes. These first stellar black holes weighed between 10 and 100 solar masses. This is small by cosmic standards, but they were the seeds. Given enough time and enough food, they could grow much larger. Vast clouds of gas drifted nearby them in space. Cosmic dust also accumulated around them over time. The black holes pulled all of this matter in with their gravity. They gained weight like a team of cosmic bodybuilders. When two galaxies eventually merged with each other, their central black holes would eventually find each other. They would spiral together over millions of years of time. Then they would merge in a catastrophic collision, a collision that would send gravitational waves rippling across space. The merger of the two black holes created a larger one. Two 100 solar mass black holes become one 200 solar mass black hole. This is just a matter of simple cosmic addition. This process has repeated throughout all of cosmic history. Merge, eat, over and over again. Over billions of years, the light seeds grew into supermassive black holes. They grew to weigh millions or billions of solar masses. They took up residence at the centers of their host galaxies. They grew alongside their hosts in a cosmic partnership. The galaxy and the black hole evolved together over time. This theory made a great deal of logical sense. It matched all of the observations in the nearby universe. It explained why bigger galaxies tend to have bigger black holes. It fit the accepted timeline of cosmic evolution. Everything about the theory worked perfectly well, until the James Webb Space Telescope started looking at the early universe. The telescope's powerful infrared vision can peer back through time. It can peer back to when the universe was very young. The telescope has detected galaxies that formed just a few 100 million years ago, and in the centers of many of these infant galaxies, blazing brightly there, sat supermassive black holes. Black holes with billions of solar masses were found. The astronomers who found them ran the numbers again and again. They checked all of their calculations for any errors. They verified all of their measurements carefully. The conclusion that they reached remained unavoidable. These ancient black holes were simply too massive, too early. Starting with a 10 solar mass seed and feeding at the maximum rate, a black hole might reach 1,000 solar masses after 100 million years. After 500 million years, maybe 10,000 solar masses. To reach 1 billion solar masses would take at least 1 billion years. 1 billion years of continuous maximum rate feeding. But the telescope found billion solar mass black holes. It found them when the universe was only 500 to 800 million years old. The light seed theory simply cannot explain them. There was not enough time for them to grow so large. Even if every single condition for their growth was perfect. Even if these black holes never stopped eating for 1 second, they could not have grown that large that fast. Some scientists tried to salvage the existing theory. Maybe the black holes could exceed the Eddington limit. They could do so under some very special conditions. Maybe they could feed much faster than we thought possible. Maybe the first stars were even more massive than our simulations predicted. This would create bigger seed black holes at the start. These modifications to the theory helped a little bit, but the timeline for their growth still did not work. The numbers stubbornly refused to add up correctly. The light seed theory was not wrong exactly. It described how many black holes in the universe grow, but it could not explain the giants that the telescope kept finding. Something else had to be happening in the early universe. A different path for their formation, a kind of cosmic shortcut. Scientists needed a way to create massive black holes quickly, without having to wait for billions of years of slow growth and mergers. They needed what are called heavy seeds for the black holes, and that led them to one of the most controversial ideas in astrophysics. The James Webb Space Telescope has become a problem-making machine, and the entire astronomy community is now scrambling to keep up. Every few months, the telescope spots another supermassive black hole, a black hole that should not exist at such an early time. Ancient quasars are seen blazing in the cosmic dawn. Black holes are seen powering galaxies when those galaxies were barely formed. These are cosmic monsters that have broken the growth rate limit. Consider the quasar J0313-1806. This object sits so far away from us in space. We see it as it was just 670 million years after the Big Bang. At its heart sits a black hole weighing 1.6 billion solar masses. That is billion with AB, an almost unimaginable mass. The telescope has now confirmed dozens of similar objects. They are scattered all across the very early universe. They are all powered by impossibly massive black holes. The paradox of their existence cuts very deep. Black holes need a great deal of time to grow. Food in the form of gas and dust must fall into them. The matter must accumulate over very long periods of time. Even at their maximum feeding rates, this growth takes time. But these early universe black holes do not have any time. They exist during the infancy of the entire cosmos, yet they have somehow already reached their full adulthood. It is like finding a fully grown blue whale swimming in an ocean that was created only yesterday. Scientists have tried every single workaround they could imagine. Maybe the seed black holes started out bigger than we thought. Maybe the first stars were absolute giants creating larger seeds of hundreds of solar masses instead of just tens. That helps the theory, but it is not enough to solve the problem. Starting with a 100 solar mass seed only buys you a little extra time. You still cannot reach billions of solar masses in just 600 million years. Maybe the black holes were able to feed much faster. Maybe they exceeded the Eddington limit by a factor of 10 or 100. Super Eddington accretion does happen in some extreme circumstances, but maintaining that feeding rate continuously for hundreds of millions of years, this seems to be physically impossible to do. The radiation pressure should blow away the surrounding gas. It should cut off the food supply for the black hole. Maybe the black holes merged more frequently than our simulations predict. Every merger can instantly double the mass of a black hole. This would skip the slow and tedious eating process. But galaxy mergers also take a great deal of time to complete. The black holes need millions of years to spiral together. This happens after their host galaxies have already collided. You cannot pack enough of these mergers into the early universe timeline, not enough to explain the existence of these giants. Every single solution that has been proposed creates new problems. Every patch that is put into the theory opens up another hole. The light seed model, which worked beautifully for nearby black holes, it fails spectacularly when it is applied to the early universe. Something fundamental is wrong with our understanding of the process. This paradox has frustrated scientists for many years. Conferences have featured very heated debates about it. Research papers have proposed increasingly exotic solutions. Some scientists suggested that we needed to modify general relativity. Others argued that our cosmological timeline must be wrong. Maybe the universe is actually much older than we have calculated. Maybe the laws of physics behave differently in the early cosmos. But most scientists suspected a much simpler answer. Maybe black holes have two different formation pathways. The light seed path works just fine for typical black holes. It explains the millions of stellar mass black holes in galaxies. It accounts for the supermassive black holes in modern galaxies, galaxies that have had billions of years to grow their black holes. But for the early universe, giants, maybe nature, found a shortcut. Maybe under some very special conditions, gas clouds could collapse. They could collapse directly into massive black holes, without having to form stars at all in the first place. No waiting for stellar death, and no slow accumulation of mass, just a rapid and catastrophic gravitational collapse. A collapse that creates a black hole weighing 100,000 solar masses. These heavy seeds could then grow to billions of solar masses. They could do so in the limited time that was available. Starting big means that you can reach a giant size much faster. The math works out if you begin with 1 million solar mass seed. The timeline then fits all of the new observations. The problem, however, was that nobody had ever seen it happen. Direct collapse remained a purely theoretical idea, a mathematical possibility that might occur in computer simulations, but it had never been confirmed in the real universe. Scientists needed some direct observational evidence for it. They needed to catch a heavy seed in the very act of forming. The infinity galaxy might finally provide that evidence. But first, scientists needed to understand a key problem. They needed to know what prevents gas clouds from forming stars. Imagine trying to build a massive cathedral in a single day. That is essentially what the early universe black holes accomplished. They reached sizes that should require billions of years of construction. But they existed when the universe was less than 1 billion years old. The math becomes much clearer when you break down the timeline. You need to know exactly how long black hole growth takes. A black hole grows by pulling in matter from its surroundings. Gas spirals inward through an accretion disk. It gradually crosses the point of no return. This point of no return is known as the event horizon. Once the matter crosses that boundary, it is gone forever. It is added to the total mass of the black hole. This seems simple enough in principle, but physics imposes limits. It imposes very strict limits on how fast this can happen. The Eddington limit defines the maximum rate of accretion. As gas falls inward, friction heats it to millions of degrees. That hot gas then radiates enormous amounts of light. The outward radiation pressure pushes against the infalling gas. At some point, the outward push balances the inward pull. That balance point is what is known as the Eddington limit. For a 10 solar mass black hole, the Eddington limit is a specific value. It allows the black hole to roughly double its mass. It can do so every 45 million years of time. That sounds pretty fast, but watch what happens when you run the timeline. After 45 million years, you have 20 solar masses. After 90 million years, you have 40 solar masses. After 135 million years, you have 80 solar masses. After 1 billion years of feeding continuously at this limit, you would reach a mass of about 30 million solar masses. That is an impressive amount of growth for a black hole, but it is nowhere near the billion solar mass monsters that the telescope finds. It is not even close to being that massive. You would need roughly 5 billion years to reach 1 billion solar masses. This is starting from a 10 solar mass seed at the beginning. Scientists have run thousands of simulations trying to find a way around this. Maybe if the seed black holes started out larger, say 100 solar masses, instead of just 10, they could reach bigger sizes a bit faster, but that only gains you one single doubling time. You still cannot reach billions of solar masses in just 600 million years. Maybe the black holes were able to feed at 10 times the Eddington limit. Super Eddington accretion does occur in nature sometimes. Some black holes can manage to pull in gas faster than the radiation pressure, especially if the gas is falling in from many directions at once. But maintaining this super Eddington accretion continuously for millions of years, this seems to be physically implausible for any black hole. The system should stabilize back to a normal feeding rate. It should do so relatively quickly over time. Maybe the early universe had more available gas for black holes to eat. It is true that the galaxies were more gas-rich back then, but more available food does not mean the black hole can eat faster. The Eddington limit depends on the black hole's mass, and it depends on the physics of the radiation pressure. It does not depend on how much food is sitting nearby. Every single attempted solution to this problem has hit a wall. The timeline for their growth remained stubbornly wrong. Black holes simply cannot grow from stellar mass seeds to billions of solar masses, not in the limited time that was available to them, not through accretion and not through mergers of other black holes, not through any combination of the normal growth processes. This time crunch has forced scientists to consider some alternatives. If black holes cannot grow from small seeds to giant sizes fast enough, then maybe they do not start out small in the first place. Maybe they actually start out very big from their birth, heavy seeds weighing 100,000 to 1 million solar masses. These would have a massive head start in their growth. Beginning with a 1 million solar mass seed, you can reach a billion. It takes less than 500 million years of feeding. The numbers finally work, and the timeline finally fits. Heavy seeds are able to solve the paradox very elegantly. But how do you create a million solar mass black hole? How do you do it without any stellar death and slow growth? You need a completely different formation mechanism. You need the process of direct collapse to occur. And you need to solve one massive and fundamental problem. Gas clouds naturally like to form stars, not black holes. Direct collapse offers an elegant solution to the early universe paradox. Instead of starting with a small stellar mass black hole and waiting for billions of years for it to grow larger, nature could have just skipped ahead in the process. Under the perfect conditions, a massive cloud of gas might collapse. It might collapse directly into a black hole that weighs 100,000 to 1 million solar masses. There would be no star formation and no supernova explosion, just pure and catastrophic gravitational collapse. A collapse that creates a heavy seed in one single event. The physics behind this process is quite straightforward. Take a gas cloud that weighs millions of times the sun's mass, make it dense enough, and make it massive enough. Gravity will eventually overwhelm all of the other forces. It will crush the entire cloud into a new black hole. It is the same process that forms stars in the universe. It is just taken to an extreme and final endpoint. When a normal gas cloud collapses, it will fragment. It will fragment into thousands or millions of smaller pieces. Each of these pieces will then become a new star. The cloud does not stay together as one single object. It breaks apart because of cooling and turbulence. These processes create density variations within the cloud. The dense spots in the cloud will collapse much faster. they will pull matter away from the less dense regions. The result is a large cluster of stars, not a single massive object. But if you change the conditions in the clouds slightly, the whole story can change in a dramatic way. If you can prevent the gas from cooling down efficiently, the gas will stay hot as it is collapsing. Hot gas has a much higher internal pressure, and more pressure will resist the process of fragmentation. The cloud can then collapse as a single coherent mass. It will not break into many smaller pieces as it does so. If the collapse proceeds fast enough, the center of the gas cloud, it will reach densities and temperatures where new physics takes over. Quantum mechanics and general relativity will then take over, at densities around 10 million grams per cubic centimeter and temperatures of 10 billion degrees Celsius. The gas undergoes what is called a general relativistic instability. The object becomes its own worst enemy in this state. Its gravity becomes so incredibly intense that it can no longer support itself. It cannot support itself against any further collapse. At that point, nothing in the universe can stop the process. The core of the gas cloud will collapse catastrophically. The fabric of space itself will warp and curve under the extreme gravity. Within just a few minutes or a few hours, an event horizon will form. A brand new black hole has now been born into the universe. This newborn black hole will weigh 100,000 solar masses. It will weigh this much right from its very first moment of existence. That heavy seed can then begin the process of normal accretion. It can grow at the Eddington limit like any other black hole, but it starts out with a massive advantage over the others, beginning with 1 million solar masses instead of just 10. This means that reaching billions of solar masses becomes possible. It becomes possible within the early universe timeline. The time crunch that was a problem completely disappears. Computer simulations have shown that direct collapse can work. It can work at least in principle in the simulations. Scientists have run detailed models of gas clouds collapsing. They have done so under very idealized physical conditions. The simulations are able to produce heavy seed black holes. They produce black holes that match the predicted mass range. The physics of the process checks out, and the math works. Direct collapse is a physically possible thing to happen, but possible does not mean that it is a common event. It does not even mean that it actually happens in the real universe. The simulations make many assumptions and simplifications. They are modeling perfect and ideal physical conditions. Nature, on the other hand, is very messy and complicated. Just because a process works on a powerful computer, it does not guarantee that it occurs in reality. Scientists needed to find a direct collapse black hole in the wild. They needed to catch one in the very act of its formation, or they needed to find one that was so young that it could not have formed. It could not have formed through the process of normal stellar evolution. They needed some evidence that went beyond just theory and simulation. The search for this evidence focused on the early universe. If direct collapse occurred anywhere in the cosmos, it would be in the first billion years of cosmic history. That is when the conditions for it were just right. That is when the universe needed heavy seeds to explain the quasars, the supermassive black holes that the new telescope keeps finding. Researchers had identified a few candidate objects for this, objects that might be direct collapse black holes. Some X-ray sources in distant galaxies had certain properties that were consistent with being heavy seeds, but the evidence for them remained very ambiguous. The observations could also be explained by other phenomena. Nothing definitive had emerged until the Infinity Galaxy, until two colliding galaxies created a natural laboratory, a laboratory for direct collapse right where we could study it, until a black hole appeared between the galaxy cores, a location that demanded a new explanation. But there is still a fundamental problem with this idea, a problem that applies to all of the direct collapse scenarios. Gas clouds in the universe like to form stars. Understanding why the gas sometimes does not form stars, this became the key to the entire cosmic mystery. Gas clouds are the star factories of the universe. If you put enough gas in one place, new stars will be born. It is one of the most reliable processes in the entire cosmos. Gravity pulls the gas together into a collapsing cloud. The cloud then collapses and begins to heat up, and eventually the process of nuclear fusion will ignite. A brand new star then lights up in the darkness. This is happening constantly throughout every single galaxy. Star formation is a natural and inevitable process, and it is extremely difficult to prevent from happening. That fact creates a huge problem for the direct collapse theory. If you want a gas cloud to collapse into a black hole, instead of forming a multitude of stars, you need to be able to stop the star formation process. The cloud must stay together as one single massive object. It cannot be allowed to fragment into thousands of pieces. A single fragmentation event can ruin the entire process. One newborn star can trigger a cascade of star formation, a cascade that can consume the entire gas cloud. So what can prevent this process of fragmentation? What can keep a gas cloud coherent during its collapse? The answer to this involves molecular hydrogen. It is one of the simplest molecules in the entire universe. Just two hydrogen atoms that are bonded together. But this simple molecule controls the fate of collapsing gas clouds. Molecular hydrogen is an extremely efficient cooling agent. When gas clouds collapse, the gravitational compression heats them up. That heat then creates a pressure that resists further collapse. The cloud wants to bounce back like a squeezed spring, but if the gas can cool down efficiently, it can radiate away that heat. The pressure inside the cloud will then drop, and the process of collapse can then continue. Molecular hydrogen is able to cool the gas through quantum transitions. The molecule can rotate and vibrate in specific patterns. When it shifts from one of these patterns to another, it releases a tiny amount of energy as infrared light. That infrared light then escapes from the cloud. It carries all of the excess heat away with it. The gas cools down, and cool gas fragments very easily. Here is the key insight into this whole process. If you can destroy the molecular hydrogen in the cloud, the gas will not be able to cool down efficiently. Only the atomic hydrogen will remain in the cloud. And atomic hydrogen is a terrible cooling agent. Without the presence of any molecular hydrogen, the collapsing gas will stay hot as it is collapsing. Hot gas has a very high internal pressure, and a high pressure prevents the process of fragmentation. The cloud can then collapse as a single coherent mass, so scientists needed to find a way to break apart the molecular hydrogen. The solution to this problem is ultraviolet light, specifically ultraviolet light in a certain wavelength range, a range that is called Lyman-Werner radiation. This radiation is able to tear the molecular hydrogen molecules apart. It splits them back into their individual atoms. It is not quite energetic enough to ionize the atoms. It is just energetic enough to break the molecular bonds. In the very early universe, the conditions were perfect for this. The very first stars produced an intense amount of Lyman-Werner radiation. That powerful radiation then flooded all of the nearby gas clouds. It destroyed all of their molecular hydrogen in the process. Those irradiated clouds were then unable to cool down. They were unable to fragment into smaller pieces. They were then primed for the process of direct collapse. But there is a catch to this entire scenario. The gas clouds also need to be completely pristine. They must be made of pure hydrogen and helium only. There can be no heavier elements present in the gas. Elements like carbon, oxygen, and nitrogen are very efficient coolants. Just a tiny contamination of these metals is enough. It allows the gas to cool down rapidly, even without molecular hydrogen. 1 part in 100,000 is enough to ruin the direct collapse. In the early universe, this condition was easily met. The first generation of stars formed from pure primordial gas. They then exploded as supernovae and scattered heavy elements. They scattered them into the surrounding space around them, but some of the gas clouds remained in a pristine state. They were protected from any metal contamination. Some clouds sat in just the right locations in space. They were bathed in the Lyman-Werner radiation from nearby galaxies, but they were also shielded from the metal-enriched supernova ejecta. Those special clouds could then undergo the process of direct collapse. They represented rare environments where all the conditions aligned: intense ultraviolet radiation, no molecular hydrogen and no metal contamination, and also the presence of massive gas reservoirs. These clouds existed during a very brief window in cosmic history, a window when the universe was between 100 and 500 million years old. After that window of opportunity had closed forever, the process of direct collapse became nearly impossible. The star formation in the universe enriched it with metals. Supernova explosions scattered the heavy elements everywhere. Finding any pristine gas clouds became increasingly difficult. The Lyman-Werner radiation background remained very strong, but the metal contamination had poisoned most of the collapsing clouds. The opportunities for direct collapse vanished as the universe aged. Modern galaxies exist in a very metal-rich environment. The space that is between the galaxies contains enriched gas. It is enriched to several percent of the solar metallicity. The star-forming regions show an even higher metal content. Finding the pristine metal-free gas that is required for direct collapse, this seems to be completely impossible in the local universe. That is what made the Infinity Galaxy discovery so shocking. Here sat a potential direct collapse black hole. A black hole that was forming not in the early universe, but in a relatively recent time in cosmic history. The collision that created it occurred billions of years ago. But billions of years after the supposed window for direct collapse had closed, the gas in the collision zone should be very metal-enriched. The physical conditions should be completely wrong for this. Yet somehow the collision had created the right environment. The violent shock waves between the colliding galaxies mimicked the early universe. They did so through a completely different physical mechanism. Instead of Lyman-Werner radiation preventing molecular hydrogen formation, turbulence and pressure were preventing the star formation directly. The collision had generated a brand new pathway to direct collapse, one that does not require the presence of pristine primordial gas. The team of researchers realized they might be watching a new formation mechanism, a mechanism that can work in any cosmic era. Direct collapse might not be limited to the early universe after all. Two spiral galaxies crashed into each other billions of years ago. It was a cosmic traffic accident that would rewrite black hole physics. They did not just sideswipe each other or merge together gradually. They collided completely head-on with each other. Both of the galaxy disks were perfectly aligned for the impact. They slammed together at speeds exceeding 600,000 miles per hour. The impact released an amount of energy equivalent to billions of supernovae. Spiral galaxies are flat disks of stars, gas and dust. They are rotating around a central core of older stars. Imagine two large dinner plates that are spinning through space. Now imagine them hitting each other edge first at a tremendous velocity. That is what happened in the case of the Infinity Galaxy. The galaxies were not destroyed in the collision, but they were transformed. The stars in each of the galaxies passed through each other. They were relatively unscathed by the violent event. Stars are incredibly tiny compared to the vast distances between them. Even in the densest parts of galaxies, stars are separated by light years. During galaxy collisions, direct stellar collisions are extremely rare. Most of the stars will sail right through the chaos, completely unharmed. They do get flung into new orbits and are accelerated by gravity, but they do not actually crash into each other. The gas in the galaxies is a completely different story. The gas clouds in each of the galaxies occupied the same space. They could not simply pass through each other like the stars did. They collided with a tremendous and violent force. The shock wave from that collision compressed the gas. It compressed it to extreme densities that are rarely seen. The temperatures of the gas spiked into the millions of degrees. Powerful pressure waves rippled outward from the impact zone. That compression then launched new waves of star formation. The shock compressed the diffuse gas into dense clouds, and those clouds immediately began to collapse into new stars. Thousands of massive young stars ignited all at once. They created the brilliant blue regions that are visible in the image. These are the ring structures that surround the galactic cores. Those rings mark where the density waves triggered violent star birth. The collision also ejected most of each galaxy's stars. It ejected them outward into those ring-like structures. The conservation of angular momentum flung the material away. It flung it away from the central impact zone. The two galactic cores contained the oldest and most tightly bound stars. They managed to survive the collision relatively intact. They now sit in the centers of the bright ring structures. They are represented as the yellow regions in the telescope's image. Between those two surviving cores stretches the collision zone. A long bridge of gas has been caught between the two galaxies. This is where the physical conditions became truly extraordinary. This is where the recipe for direct collapse finally emerged. The head-on collision generated extreme turbulence in this gas bridge. Powerful shock waves crisscrossed the entire region. The gas streams from both of the galaxies met and mixed violently. The density fluctuations in the gas created chaotic pressure variations. The entire zone became a maelstrom of turbulent gas that was moving at supersonic velocities. That high level of turbulence prevented normal star formation. Usually, the process of star formation proceeds very smoothly. A dense region of gas accumulates more gas through gravity. It then fragments into many smaller pieces over time. Each of these pieces then collapses and ignites nuclear fusion. But in the collision zone, the turbulence disrupted this process. Before the gas, clouds could accumulate and collapse into stars. The powerful shock waves were tearing them apart. The pressure variations prevented any stable fragmentation patterns. The collision also compressed the gas to extraordinary densities. Normal interstellar gas contains about 1 atom per cubic centimeter. That is essentially a perfect vacuum by our standards on Earth. But in the collision zone, the densities reached much higher values, thousands or even millions of atoms per cubic centimeter. That compressed gas had a tremendous amount of mass. It was concentrated in a relatively small volume of space. High density plus high turbulence equals the perfect conditions. The perfect conditions for the process of direct collapse. The gas could not form stars because the turbulence prevented fragmentation. The gas could not disperse because the density and gravity held it together. The gas could only do one thing in this situation. It could continue to collapse under its own immense weight. It would continue to do so until something fundamental happened, and something fundamental did indeed happen in this case. The force of gravity won the battle in the end. The center of that gas bridge reached extreme densities and temperatures. A general relativistic instability was then triggered. The core of the cloud collapsed catastrophically and completely. An event horizon formed, and a new black hole was born. A black hole was born in the space between the two galaxies. The collision had created a modern analog to the early universe, an analog to the direct collapse conditions that once existed. Instead of Lyman-Werner radiation preventing molecular hydrogen formation, turbulence was directly preventing the process of star formation. Instead of pristine primordial gas collapsing under gravity, metal-enriched modern gas was collapsing under extreme pressure. The physical mechanism differed, but the final result remained the same. A heavy seed black hole had formed in one single rapid collapse event. The space between the two colliding galaxies became a pressure cooker that was operating on truly cosmic scales. The gas from both of the galaxies met in the middle. It created a dense bridge of material that was under extreme compression. Understanding what happened in this zone requires understanding shock waves and understanding how they are able to transform gas. When two gas clouds collide at a very high velocity, they do not just bounce off of each other like billiard balls. They interpenetrate each other briefly, then a shock wave forms. A shock wave forms at the collision interface between them. Think of two large walls of water that are rushing toward each other. When they meet, the water does not simply reflect backward. It piles up into a towering wall where the two streams meet. That is similar to what happened here, except the water is hydrogen gas, and the velocity is 600,000 miles per hour. The shock wave from the collision compressed the gas to high densities that far exceeded the normal interstellar conditions. This compression then heats the gas through a process called adiabatic heating. If you squeeze a gas into a smaller volume, its temperature will rise. The collision zone was heated to millions of degrees initially. That is hot enough to strip the electrons from the atoms. This creates a hot ionized plasma in the region. This ionized gas then glows brightly, which we can see. It is the green bridge that is visible in the telescope's image. But the temperature of the gas does not stay constant. The gas will radiate away its heat through various processes. In normal circumstances, the gas would cool down rapidly. It would then form a multitude of new stars in the process. The compression would trigger a period of intense star formation. It would convert the gas into thousands of new stars. This would happen within just a few million years, but the presence of the turbulence changed everything. The collision did not create a smooth, uniform compression. It generated chaotic and turbulent flows of gas. Eddies and vortices were formed at every single scale. The gas streams crossed each other at different angles. Density fluctuations appeared and then disappeared over time. That turbulence then injected energy into the gas continuously. Every time the gas parcels collided with each other, every time the shock waves crisscrossed the region, they pumped a great deal of kinetic energy into the system. This energy in the form of heating balanced the radiative cooling. The gas was not able to cool down efficiently. This was because the turbulence kept reheating it. The temperature of the gas remained high enough to prevent star formation. Scientists can measure the level of turbulence in a gas. They use a quantity that is known as the Mach number. It compares the velocity of the gas flows to the speed of sound. Mach 1 means the gas is moving at the speed of sound. Mach 2 means it is moving at twice the speed of sound. Supersonic turbulence means that the Mach numbers are above 1. The infinity galaxy's collision zone exhibits very high Mach numbers. They are between 5 and 10 based on the spectroscopic measurements. That is an extremely turbulent environment for a gas cloud. The gas streams are moving 5 to 10 times faster than sound waves. This supersonic turbulence is creating powerful shocks everywhere. The entire region is a complex network of intersecting shock waves. They are constantly processing all of the gas in the region. This high level of turbulence prevents fragmentation. It does so through a mechanism called turbulent pressure support. Normally, gravity tries to pull the dense regions together, while the thermal pressure is pushing them apart. When gravity wins this battle, the region will collapse. It will collapse and form a new generation of stars. But if you add strong turbulence, you add a third pressure component. The turbulent motions of the gas create an additional outward pressure. This pressure resists the gravitational collapse on small scales. The dense clumps of gas that are trying to form stars get disrupted. They are disrupted by the turbulent flows of the gas. The shock waves in the region tear them apart completely. Velocity shears will stretch them out into long filaments. The gas simply cannot settle into stable star-forming configurations. It remains in a state of violent and chaotic motion. But the force of gravity still works on the large scales. The entire gas bridge is gravitationally bound as a whole. Even though the turbulence is preventing the small-scale collapse into stars, it does not prevent the large-scale collapse of the entire structure. The bridge as a whole continues to contract under its own gravity. Mass continues to accumulate in the very center of the region. This creates the precise conditions needed for direct collapse. A massive gas reservoir is collapsing as a single coherent object. It has high temperatures from compression and turbulent heating. There is no star formation due to the turbulent disruption. All of the necessary ingredients have assembled in one single place. The compression zone measured thousands of light years across, but it contained enough mass to form millions of stars. Instead of that, all of that mass was funneled into the center. The density in the center kept rising and the pressure kept building. Something in the system had to give way eventually. The core of the gas cloud reached extreme densities. Quantum mechanics and general relativity then dictated the outcome. The gas cloud had crossed a point of no return. An event horizon formed, and the compression zone had birthed a black hole. The turbulence in the infinity galaxy's collision zone is extreme. It is at a level that is rarely seen in the universe. It is not a gentle stirring of the gas, but violent chaos. It is approaching the theoretical maximum possible for cosmic gas clouds. This extreme turbulence became the key factor in preventing star formation and in enabling the process of direct collapse to occur. Understanding why this is requires understanding what turbulence does, what it does to a gas cloud on different physical scales. At the very largest scales, the turbulence will mix the material. The gas from one galaxy will blend with the gas from the other. This mixing will homogenize the composition of the gas. It will spread the metal-enriched gas throughout the collision zone. In a sense, the turbulence makes the gas more uniform on large scales. Even while it is creating density fluctuations on small scales, at the intermediate scales the turbulence creates filaments and sheets. The gas does not stay uniformly distributed in the cloud. It concentrates into thread-like structures and planar features. These structures are constantly shifting and evolving over time. The filaments will fragment, and then they will reconnect. The sheets will ripple, and then they will tear apart. The collision zone resembles a tangled web of gas. It does not resemble a smooth and uniform cloud of gas. At the very smallest scales, the turbulence generates eddies and vortices. These are spinning regions of gas that are like tiny whirlpools. In normal star-forming regions, these eddies would collapse. They would collapse and form individual new stars. But in the collision zone, the turbulent velocity is too high. The eddies are torn apart before they can collapse. Every single attempt at star formation is disrupted by the violent motions. Scientists can measure the turbulence by looking at the spectral line widths. When a gas emits light at a specific wavelength, that light will be Doppler shifted by the gas's motion. Gas that is moving toward us will be shifted to shorter wavelengths. Gas that is moving away will be shifted to longer wavelengths. In a calm region of space, all of the gas moves at similar velocities, so the spectral line that is emitted will be very narrow. In a turbulent region, different parts of the gas are moving at different velocities, so the spectral line will broaden out significantly. The infinity galaxy's collision zone shows very broad spectral lines. They are broadened by velocities exceeding 600 miles per second. For comparison, typical star-forming regions show much narrower lines. Line broadening of just a few miles per second is normal. The collision zone is roughly 100 times more turbulent than the normal star formation sites that we see. That is an extreme level of turbulence even for galaxy collisions. This turbulence must be driven by some input of energy. Turbulence will naturally decay over time as its energy is converted. Kinetic energy is converted to heat through friction and viscosity. For the turbulence to persist, something must continuously inject energy. In the collision zone, multiple energy sources are feeding the turbulence. The ongoing collision between the two galaxies provides the primary energy. The two galaxies have not yet finished their merging process. Gas streams are still flowing from both of the galaxies. They are flowing into the central collision zone between them. Every time that new gas enters this region, it adds kinetic energy. The collision continues to pump energy into the system. It does so billions of years after the initial impact. The shock waves in the region provide a secondary energy input. Each shock will convert the organized flow of the gas into random motion. The collision zone contains countless shock waves that are propagating. They are propagating in many different directions. They intersect and they interact with each other. They create complex patterns of energy dissipation and turbulence. It is a kind of cascade process in the gas. Large shocks will create smaller shocks in the flow. The smaller shocks will then create the turbulent eddies. The entire system is able to self-sustain its own turbulence. Gravity itself also contributes to the process. As the gas bridge contracts under its own immense weight, gravitational potential energy is converted to kinetic energy. The material falls inward and it accelerates as it goes. This infall motion then adds to the turbulent velocity field. Gravity is fighting to compress the gas, and the turbulence is fighting back. It is fighting to disrupt the gas and blow it apart. The delicate balance between these two forces determines the outcome. If the turbulence dominated completely, the gas bridge would disperse. The random motions would overcome the force of gravity. The gas would be blown apart into intergalactic space. But the turbulence does not completely dominate in this case. Gravity is winning the overall battle for control, even though the turbulence is winning on the small scales. This creates a kind of hierarchy in the system. On the small scales, the turbulence is preventing star formation. On the large scales, gravity is driving the continued collapse. The gas bridge contracts as a whole while remaining too turbulent. It is too turbulent to fragment into individual stars. This hierarchy is exactly what the direct collapse theory requires. The turbulence also ensures that the gas has high temperatures. Every single shock wave in the region will heat the gas. Every collision between the turbulent eddies converts kinetic energy. It converts it into thermal energy, which is heat. The gas stays hot and it maintains a high pressure. The high pressure then prevents cooling and fragmentation. It does so through an additional mechanism beyond the turbulent disruption. Scientists have realized that this collision created a natural laboratory, a laboratory for testing the theory of direct collapse. The conditions here differ from the early universe scenario, but the essential physics of the process remains the same. You must prevent star formation, and you must maintain high temperatures. You must also compress a massive amount of gas into a small volume. Then you just let the force of gravity do the rest of the work. The mechanism for preventing the star formation differs, but the final result of the process is identical. A heavy seed black hole is formed through direct collapse, somewhere in the chaos of the collision zone. At some moment, that was billions of years ago, something crossed a critical threshold in the system. The gas was compressed beyond a certain critical density. The temperature and the pressure reached some extreme values where the normal physics of matter breaks down. The laws of general relativity then took full control. An event horizon formed, and the universe had gained a new black hole. This formation event happened very quickly by cosmic standards. From the moment the gas cloud reached the critical conditions to the moment that a black hole existed in its place, this probably took less than one single year to happen. It might have been as little as just a few months. Theoretical models suggest that the final collapse proceeds. It proceeds at nearly the speed of light itself. Once the general relativistic instability is triggered, absolutely nothing in the universe can stop it. The formation sequence of the black hole follows a specific pattern. First, the core of the gas cloud reaches very high densities of around 1 million grams per cubic centimeter. That is very dense for a gas cloud, but it is still far below the density of the atomic nuclei. At these densities, the core of the gas cloud becomes opaque. It becomes opaque to its own radiation that it is emitting. The photons that are produced cannot escape from it easily. They will scatter repeatedly off of the electrons and atoms. The core of the cloud becomes trapped by its own light. Second, the trapped radiation pressure will briefly halt the collapse. The core of the cloud will reach a quasi-stable state, a state that will last for perhaps a few thousand years. Matter will continue to fall onto this stable core. It will fall from the surrounding gas in the cloud. The envelope of the object will grow more and more massive, while the core of the object stays relatively constant. Scientists call this strange configuration a quasi-star. It is not quite a star because fusion does not dominate its energy. It is not yet a black hole because an event horizon has not formed. It is an intermediate state that is unique to direct collapse. Third, as the mass of the envelope increases over time, the core of the object gets squeezed even harder. This compression will raise the temperature of the core. The normal matter cooling mechanisms cannot remove the heat. They cannot remove it fast enough to keep up. The core temperature will then climb to 1 billion degrees Celsius. At these incredibly high temperatures, a new cooling mechanism activates. This new mechanism is called neutrino emission. Neutrinos are ghostly particles that barely interact with matter. They can escape from regions that are so dense that even light gets trapped. When matter reaches temperatures above 1 billion degrees, it will produce neutrinos through various quantum processes. Those neutrinos will then carry away enormous amounts of energy. They provide a cooling mechanism that works even in the densest regions. Fourth, this neutrino cooling will trigger a catastrophic collapse. The core of the object will lose its pressure support. It will lose it as the neutrinos carry away all of the heat. The temperature will drop even as the density is increasing. This violates the normal relationship between these two quantities. Under normal circumstances, compressing a gas will heat it up. But with neutrino cooling compressing, a gas can cool it down. This thermal instability will then cause a runaway collapse. Fifth, the core of the object will collapse inward. It will collapse at nearly the speed of light itself. Within just a few hours or a few days, it will shrink. It will shrink from the size of our solar system to the size of a city. Then it will shrink to the size of a basketball. Space itself will warp under the extreme force of gravity. Time dilation will become very severe near the object. An outside observer would see the collapse slow down and freeze. It would freeze as the matter approaches the event horizon. But from the perspective of the infalling matter itself, the collapse will proceed at a breakneck speed. Finally, the event horizon will form around the object. A boundary in spacetime will appear, marking the point of no return. Anything that crosses this boundary can never escape. The new black hole has finally been born into the universe. Its initial mass might be around 10 to 20 solar masses, just the core material that had collapsed first. But it sits in the middle of a massive envelope of gas, an envelope that is still falling inward toward it. That envelope will provide enormous amounts of matter for rapid accretion. The newborn black hole will begin to feed immediately. The surrounding gas does not just magically disappear, it will continue to fall inward now into the new black hole. It will no longer be falling onto a quasi-star core. The accretion rate at this stage is truly tremendous. It will far exceed the normal Eddington limit for a black hole. The black hole will gain mass very rapidly at this stage. It will double in weight every few months of time. Initially, this super Eddington growth phase will last. It will last until the radiation from the accretion disk becomes powerful enough to blow away the remaining gas envelope. At that point, the black hole will emerge from its cocoon. It will be revealed as a bright X-ray and radio source. It will be embedded in a cloud of ionized gas. This is the state that the infinity galaxy's black hole is in. It is now actively feeding and still growing larger, but it is no longer buried in an optically thick envelope. The team calculated that the formation event occurred recently. It occurred recently in the galaxy collision's timeline. The black hole is therefore very young and it is still growing. It is still changing over time as it consumes more mass. This makes it an incredibly valuable object for studying direct collapse. It has not had enough time to grow enormously large, nor has it had time to merge with any other black holes. It represents something that is close to a pristine heavy seed. Everything about this discovery hinged on measuring one number. How fast is the black hole moving compared to the gas that is surrounding it in the collision zone? This single measurement would determine if the theory was correct, or if simpler explanations could account for the observations. The team knew that this velocity measurement would make or break their case. If the black hole was racing through the collision zone at a high velocity, it had probably been ejected from one of the galaxy cores. Black holes can be ejected during violent mergers. This happens through a process that is called gravitational recoil. When two black holes spiral together and then merge, the gravitational waves that they emit can carry momentum. If those waves are emitted asymmetrically in space, they can kick the newly merged black hole like a rocket. Some of these ejected black holes can travel at thousands of miles per second. This is fast enough to escape their host galaxy entirely. An ejected black hole would have a velocity that is significantly different. It would be different from the surrounding gas that it is moving through. The gas in the collision zone is moving at the orbital velocity of the two colliding galaxies. This is roughly 300 miles per second for this system. An ejected black hole might be moving at 1,000 miles per second. The velocity difference between the two would be obvious and conclusive. If the black hole sat motionless relative to the gas, that would strongly support the theory of direct collapse. A black hole that is born from the gas should share the gas's velocity. They would have formed from the very same material. They should therefore be moving together through space. A velocity match would indicate that the black hole is embedded. It would be embedded in the gas cloud, not just passing through it. The team applied for additional observation time on the telescope. They needed high-resolution spectroscopy to measure the velocities. The telescope's instruments can split light into detailed spectra. They can reveal the wavelengths of the emission lines with extreme accuracy. Those wavelengths of light encode the velocity information. They do so through the well-known Doppler effect. The observations for this finally came through for the team. They analyzed the new data with a feeling of mounting excitement. They measured the velocity of the ionized gas throughout the collision zone. The gas that was near one of the galaxy cores was moving toward us. It was moving at 270 miles per second. The gas that was near the other core was moving away. It was moving at 290 miles per second. The collision zone shows a very complex velocity field. The gas is moving at different speeds in different locations. Then they measured the velocity of the black hole itself. They used the emission lines from the hot gas in its immediate vicinity, gas that is so close to the event horizon that it must be moving with it. Those emission lines revealed a velocity of 280 miles per second. This was right in the middle of the gas velocity distribution. It was not moving fast relative to the surrounding gas. It had not been ejected, and it was not just passing through. It was completely embedded in the gas around it. The velocity match was even better than they had required. The team had proposed that if the velocities agreed within 30 miles per second, that would be strong evidence. Strong evidence for the process of direct collapse. The actual measurement showed an agreement within just 10 miles per second. The black hole is clearly moving with the gas around it. It is a part of the gas cloud, and it formed there. This result completely eliminated the ejection scenario. An ejected black hole would show obvious velocity differences. The measurement showed no such difference in the data. The black hole is not a runaway from either of the galaxy cores. The velocity test also eliminated the chance superposition scenario. If a third background galaxy existed and its black hole appeared to be there, it would appear to be there only due to projection effects. That background black hole would show a very different velocity. Background galaxies are all receding from us due to cosmic expansion. Their velocities will depend on their distances from us. A background galaxy would show a substantially redshifted velocity, a velocity that is completely inconsistent with the collision zone gas. The measurements confirm that the black hole sits physically in the zone. It is not projected from behind, and it is not racing through at high speed. It is embedded in the gas bridge between the two galaxies, and it moves with that gas as if it were born from it. The team called this result the key finding they were after. The velocity match strongly supports the direct collapse formation theory, combined with the black hole's location and its mass, and the ionized gas distribution and the extreme turbulence. The evidence points toward only one single conclusion. This black hole must have formed through the direct collapse of the gas. The team could not say for sure that they had found direct collapse. Science rarely deals in absolute certainties of this kind, but they could say that the evidence strengthened the case. It strengthened it substantially while eliminating other explanations. This might be humanity's first glimpse of direct collapse, a direct collapse that was caught in the very act. The birth of a heavy seed black hole in the modern universe. But the story of this amazing object does not end here. There is more to the infinity galaxy than one unusual black hole. The discovery gets even stranger from this point on. Scientists love rules because rules reveal the patterns in nature. The 30 miles per second rule became the threshold that separated one formation scenario from another. If the black hole's velocity differed from the gas by more than 30, the process of direct collapse would become very unlikely. If the velocity matched within 30 miles per second, direct collapse would then become the leading explanation. This simple rule was able to distill complex physics. It distilled it into one single testable prediction. Why was the number 30 miles per second chosen specifically? The number comes from understanding how gas clouds move and how black holes will interact with those clouds. The gas in the collision zone does not move uniformly. Different regions of the gas have different velocities. The turbulence in the gas creates velocity variations of about 20 to 30 miles per second. That is the natural scatter in the motion of the gas. A black hole that is born from that gas should share its average velocity. It might differ slightly due to the local velocity variations, but that difference should fall within the turbulent scatter. 30 miles per second represents a conservative upper limit. Anything within that range suggests that the black hole and the gas are coupled. An ejected black hole would tell a completely different story. Gravitational recoil kicks from black hole mergers can be very strong. They can reach 1,000 miles per second or even higher. Even a relatively gentle ejection can produce high velocities. Velocities of several hundred miles per second are common. The difference would be completely unmistakable in the data. You do not need precise measurements to tell the difference. The difference between 30 and 300 miles per second. The same logic applies to what are called runaway black holes. Sometimes, supermassive black holes can get ejected from galaxy cores. This happens through a process called three-body interactions. When three massive objects orbit each other, the system is chaotic. Eventually, one of the objects will get flung out at a high velocity. The other two will then bind together more tightly. If the infinity galaxy's black hole were a runaway, it would show a very high velocity in the measurements. Interloper scenarios also fail this crucial velocity test. Imagine a third galaxy that happens to align with the collision zone. Its central black hole would appear to sit between the two main galaxies, even though it is actually much farther away from them. But that third galaxy would have its own unique velocity, a velocity that is determined by the cosmic expansion and by its own motion through the vastness of space. That velocity would almost certainly differ dramatically. It would differ from the gas in the collision zone. The velocity measurement cut through these alternative explanations. It did so with a kind of surgical precision. One single number was able to eliminate multiple different scenarios. The team of researchers knew this when they designed their proposal. They focused their entire follow-up strategy on obtaining the best data, the highest quality velocity measurements that were possible. The spectrograph on the telescope delivered the data they needed. The instrument can measure velocities to a very high accuracy, about 3 miles per second under ideal conditions. The Infinity Galaxy observations achieved nearly that precision. The uncertainty in the velocity measurement was only about 5 miles per second. This was more than good enough to test the 30 miles per second rule. The final result of the measurement exceeded all of their expectations. The black hole's velocity matched the gas's velocity. It matched it to within just 10 miles per second. This was well within the 30 miles per second threshold. The match was so close that it essentially proved something. It proved that the black hole and the gas are moving together. They are moving as a single, unified system in space. Think about what this means for our understanding. The black hole is not just visiting this region of space. It is not just passing through on its way somewhere else. It is not projected from some distant background galaxy. It lives in the collision zone, and it was born there. Or it has been there for so long that it has coupled to the gas. Given the young age of the collision and the active feeding, the formation in place explanation makes much more sense. The 30 miles per second rule had worked perfectly. It had predicted that a direct collapse black hole should match the gas. The measurement had confirmed that prediction with high accuracy. One more piece of evidence was supporting an extraordinary claim, but the team of researchers was not done finding surprises. The Infinity Galaxy held some secrets that nobody had anticipated. The Infinity Galaxy does not host just one supermassive black hole. It actually hosts a total of 3 of them. Each of the 2 colliding galaxy cores had retained its original black hole. Both of these black holes are also actively feeding. Both of them are emitting X-rays and also radio waves. Both of them weigh millions of times the mass of our Sunday. And then there is the third black hole that is floating between them. It is floating in the turbulent collision zone. 3 supermassive black holes in one single system. This discovery emerged gradually as the team analyzed the data. The Chandra X-ray Observatory had detected 3 distinct X-ray sources, one in each of the galaxy cores and one in the middle. The X-ray emission from supermassive black holes has a signature, a characteristic signature that is easy to identify. The energy spectrum and the variability patterns are distinctive. All 3 of the sources that were detected showed these telltale signs. The Very Large Array then confirmed this picture with radio observations. 3 bright radio sources appeared in the same locations as the 3 X-ray sources that were found. Black holes are known to launch powerful jets of particles. They launch them at nearly the speed of light when they are feeding. These jets then emit radio waves through a process called synchrotron radiation. The radio detections proved that all 3 black holes are actively accreting. The infrared data from the telescope showed broad emission lines. These broad lines were coming from all 3 of the locations. Broad lines indicate that the gas is moving at extremely high velocities. Velocities of thousands of miles per second are common. Only supermassive black holes can generate such extreme velocity fields. The spectroscopic signatures confirmed 3 active galactic nuclei. 3 active galactic nuclei in one single system. This triple system is an extraordinarily rare find. Finding even 2 active supermassive black holes in one system is uncommon. They can exist when 2 galaxies collide with each other, and both of the central black holes remain active during the merger. But those are binary systems with only 2 black holes. Triple systems will require something much more unusual. The standard formation scenario for these triple black hole systems, it involves 3 different galaxies all merging simultaneously. Galaxy groups can sometimes contain several members that are close together. If three of these galaxies merge, their central black holes might all end up. They might all end up in the final merged galaxy. But the infinity galaxy shows only two distinct galaxy cores. There is absolutely no evidence of a third galaxy in the system. That leaves the process of direct collapse as the explanation. The explanation for the existence of the third black hole. It must have formed from the gas in the collision. It did not arrive with a pre-existing host galaxy. This fact makes the infinity galaxy a unique object, a merger binary plus a direct collapse heavy seed. All of them are existing in one single system. The three black holes have different masses and feeding rates. The two galaxy core black holes weigh roughly 10 million solar masses. This is based on their X-ray luminosities and the orbital velocities. They are mature, supermassive black holes that have grown over time. They grew over billions of years within their host galaxies. The collision zone black hole weighs about 1 million solar masses. This is 10 times less massive than its two companions. It is the baby of the family, and it is the youngest member. It is still growing rapidly at this point in time, while the older black holes are feeding at more sedate rates. The system's future evolution is fascinating to consider. The two galaxy cores will eventually merge completely. Their central black holes will then spiral together. They will do so over tens of millions of years. They will emit powerful gravitational waves as they orbit each other. Eventually, they will merge in a catastrophic collision, a collision that will send ripples through spacetime. These ripples will be detectable by gravitational wave observatories. But what will happen to the third black hole in the system? It might merge with one of the other two black holes. It might get ejected from the system through three-body interactions. It might even survive and orbit in the final merged galaxy. Computer simulations have suggested that all three outcomes are possible. This depends on the exact trajectories and the timing. The triple system makes the infinity galaxy a natural laboratory, a laboratory for studying the dynamics of black holes. Most systems in the universe contain only one black hole. Binary systems are already rare enough to find. Triple systems are truly exceptional and very rare. Having one member be a potential direct collapse black hole, this makes this system a one-of-a-kind discovery. The discovery also raised a number of new questions. If one direct collapse black hole formed in this collision zone, could others also be forming in other locations? Could galaxy collisions be routinely producing heavy seeds? The team of researchers started to wonder about this. They wondered if direct collapse might be more common than anyone suspected, not limited to the early universe, and not requiring pristine gas, just requiring violent enough collisions to create the right conditions. The implications of this discovery just kept on expanding. But first they needed to understand how the three telescopes worked, how they worked together to uncover this amazing system. Black holes are invisible by their very definition. Light cannot escape from inside their event horizon. So how do we ever detect them in the first place? We look for the mess that they make while they are eating, and that mess will shine very brightly in X-rays and radio waves. The Chandra X-ray Observatory and the Very Large Array were crucial. They provided the evidence that three black holes are feeding. They are feeding in the infinity galaxy system. X-rays are able to reveal the hottest material in the universe. Gas that is falling into a black hole will accelerate. It will accelerate to nearly the speed of light. Friction in the accretion disk will then heat this gas. It will heat it to tens of millions of degrees Celsius. At those incredibly high temperatures, the atoms move so fast they will collide with each other with tremendous energy. Those collisions are what produce the powerful X-rays. The hotter the gas is, the higher the X-ray energy will be. Chandra detected what are known as hard X-rays. They were detected from all three of the locations. Hard X-rays are very high-energy photons that can only be produced. They are produced by extremely hot gas or by high-energy particles. The X-ray spectra that were measured showed characteristic features. Features of black hole accretion like power law distributions. also ion emission lines and variability over time. The collision zone black hole produces about 1/10 the X-ray luminosity, 1/10 the luminosity of the two core black holes. This matches the expectations for a smaller, younger black hole. Less mass means a shallower gravitational well. Less gravitational energy gets converted to radiation during accretion. The X-ray measurements provided an independent check on the mass. The mass estimates that were made from other methods. Chandra also detected some extended X-ray emission. It was surrounding the collision zone black hole. This diffuse emission is coming from the hot ionized gas that has been heated by the shocks and the radiation. The extent of this hot gas matches the green glowing region, the region that is visible in the telescope's images. Multiple wavelengths of light are painting a consistent picture, a picture of a black hole that is embedded in a vast cloud of gas. The radio observations are telling a different but complementary story. The Very Large Array detected synchrotron radiation from all three locations. Synchrotron emission occurs when electrons are spiraling. They are spiraling around magnetic field lines at nearly light speed. These spiraling electrons will then emit radio waves. The wavelength and intensity of this emission encode information about the magnetic field strength and the electron energies. Black holes are known to generate powerful magnetic fields. They generate them in their turbulent accretion disks. These fields will then channel the particles into powerful jets that shoot outward at 90% of the speed of light. These jets can extend far beyond the accretion disk. Sometimes they can reach hundreds of thousands of light years. They can extend far into intergalactic space. They are the most energetic, continuous outflows in the universe. The Infinity Galaxy's collision zone black hole shows these radio jets. The jets are extending about 5,000 light years. They are extending in opposite directions from the black hole. The jets are plowing into the surrounding gas. They are creating shock waves that are visible in radio wavelengths. These radio lobes prove that the black hole is actively launching jets. It is launching them right now in the present moment. It is not a dormant black hole, but it is feeding vigorously. The radio jets are also able to provide velocity information. The approaching jet will appear to be brighter than the receding jet. This is due to a process called relativistic beaming. The light from material that is moving toward us gets compressed. It gets compressed and also brightened as a result. The light from material that is moving away from us gets stretched. It gets stretched and also dimmed as a result. The brightness ratio between the two jets reveals the jet velocity. The collision zone black hole is launching jets at 70% of light speed. The combined observations from all three telescopes created a complete portrait. The James Webb Space Telescope sees the ionized gas in infrared light. The Chandra X-ray Observatory sees the superhot accretion disk in X-rays. The Very Large Array sees the powerful jets in radio waves. Each of these telescopes contributes its own unique information. Together, they are able to confirm an actively accreting black hole. This multi-wavelength approach is essential for modern astronomy. No single telescope can possibly capture the full story. Black holes are known to emit across the entire electromagnetic spectrum, from the long wavelengths of radio waves to the short wavelengths of gamma rays. Each of these wavelengths reveals a different aspect of the physics. Radio waves show the jets and the magnetic fields. Infrared light shows the dust and the ionized gas. X-rays show the hottest material that is closest to the event horizon. The Infinity Galaxy observations demonstrate the power of combining data from multiple different observatories. The new telescope provided the initial discovery and the detailed infrared imaging. Chandra then confirmed the active black holes through its X-ray detection. The Very Large Array then revealed the jet structures through its radio mapping. Each of these observations strengthened the case for three active black holes. But none of this would have happened without one crucial starting point: a team of astronomers who were hunting through archival data. They were hunting for any kind of cosmic oddities. The Infinity Galaxy was hiding in plain sight for a long time. It was buried in hundreds of terabytes of telescope data. It was just waiting for someone to finally notice it. Pieter van Dokkum and Gabriel Brammer were not looking for black holes. They were hunting for anything that was weird in the data, anything that did not fit the normal patterns of galaxies, anything that made them stop scrolling and say, "What is that?" The data that they were using came from a survey called Cosmos Web. This is one of the largest surveys ever conducted by the telescope. The survey observed a region of the sky in the constellation Sextans. It captured deep images of more than 1 million galaxies. Galaxies from across all of cosmic history were seen. The observations for this survey took 255 hours. 255 hours of the telescope's precious time. This generated massive data sets for the astronomers. The James Webb Space Telescope collects far more data than any human team can analyze. It cannot be analyzed in real time as it comes in. The telescope is observing the universe constantly. The data from it flows down to the Earth continuously. That data is then archived in public databases. Any astronomer in the world can access this data. But accessing the data is one thing and looking through it is another. Actually, looking through millions of images is a huge task. The archive contains many treasures, but they are hidden. They are hidden in a vast ocean of raw data. The team developed new algorithms to search for unusual objects. They wrote computer code to identify galaxies with weird shapes, or galaxies with strange colors, or unexpected brightness patterns. The algorithms flagged thousands of candidates for them. Then came the tedious part of the process for the team. They had to visually inspect each of the candidates. They had to separate the truly interesting objects from the false alarms. They found the Infinity Galaxy during one of these inspection sessions. The unique figure-8 shape of the galaxy jumped out immediately. Galaxy mergers are a common event in the universe, but perfect symmetrical rings that form an infinity symbol are rare. Van Dokkum sent the image of the galaxy to his colleagues. Everyone who saw it agreed that this deserved a closer examination. The initial telescope image showed the two bright cores and the ring structures. But the really interesting feature was that green bridge. The green bridge of gas that was stretching between them. The hydrogen emission in it looked very intense and also very extended. Something was clearly lighting up that gas from within. The team then checked the archival data from other surveys. The Infinity Galaxy had been observed by other telescopes before. The Hubble Space Telescope and ground-based telescopes had seen it, but those observations did not reveal the details that were visible to the new telescope. The new telescope's infrared vision can cut through the cosmic dust. The dust that blocks the visible light from our view. The collision zone contains enormous amounts of cosmic dust. Dust from destroyed stars and from the gas clouds. Visible light observations can only show the brightest regions. The infrared light is able to penetrate through this dust. It reveals the full and complete structure of the object. The new telescope saw what the previous telescopes had missed. The discovery process exemplifies modern astronomy. Telescopes are generating data much faster than humans can analyze it. The James Webb Space Telescope alone produces a lot of data. It produces about 60 gigabytes of data every single day. The Hubble Space Telescope's archive contains over 175 terabytes. The upcoming Vera Rubin Observatory will generate 20 terabytes per night. We are literally drowning in a sea of cosmic data. This situation creates some amazing opportunities for discovery. Archival searches can frequently uncover objects that were missed. The original telescope operators might have been looking for something specific. They would have analyzed their targets and then moved on. Years later, someone who is searching for something completely different, they might notice an interesting background object in the data. the same data gets reanalyzed for new scientific purposes. The Infinity Galaxy existed in the telescope's data for months. It was there for months before the team finally noticed it. Other astronomers had likely seen it while scrolling through the images, but they did not recognize its full significance. It takes a great deal of experience and intuition to spot the unusual among the vast sea of the mundane. It takes knowing what kinds of questions to ask of the data. Van Dockum immediately suspected that something important was lurking in that strange collision zone between the galaxies. The symmetry of the object was just too perfect. The emission from the gas was just too bright. He contacted some of his colleagues who had access to other telescopes. They had access to Chandra and the Very Large Array. They requested some follow-up observations of the galaxy. They targeted the Infinity Galaxy specifically with these observations. Those observations then detected the 3 X-ray sources, and they detected the 3 separate radio emissions. The discovery then snowballed from that point onward. Each new observation revealed some additional details: the velocity measurements, the ionization mapping, and the jet structures. What had started as a weird-looking galaxy in an archived image, it became one of the most important black hole discoveries in recent years. This is how most of the major discoveries happen in modern astronomy. Not through targeted searches, though those are still important, but through the process of serendipity and chance, through someone noticing something odd and deciding to investigate, through algorithms that are flagging unusual candidates, and humans who are recognizing their scientific significance. The Infinity Galaxy discovery reminds us that the universe still holds surprises. We have mapped out billions of different galaxies. We have measured the expansion of the entire cosmos. We have even detected the faint ripples of gravitational waves. But we are still finding new phenomena that challenge our theories. We are still uncovering objects that should not exist. Objects that should not exist according to our current models. We are still learning that nature is more creative than our imaginations, and the Infinity Galaxy had even more secrets to reveal. The green glow that is between the galaxy cores is not uniform. It is not a smooth and featureless bridge of gas. A close examination of it reveals a great deal of structure. There are filaments, knots, and regions of varying brightness. This structure tells a story about what is happening. What is happening in the turbulent collision zone. Every single detail in the ionization pattern provides clues. Clues about the powerful black hole that is hiding within. Ionized hydrogen emits light through a specific quantum mechanical process. A free electron will be drifting through space. It will then encounter a hydrogen ion, which is just a proton that has lost its single electron. The electron then gets captured by the proton. This forms a neutral hydrogen atom once again, but the electron does not drop directly to the lowest energy level. It will cascade down through the higher energy levels first. And each of these transitions will release a photon of light at a very specific wavelength. One of these transitions produces light at 1.65 microns. This is in the infrared part of the spectrum. This is the emission line that the telescope's instruments detect, and they display it as the color green in the false color images. The brightness of this emission directly indicates something. It indicates how much of the hydrogen is being ionized. The brighter regions mean that more ionization is occurring, and more ionization means more radiation from the black hole. The brightest ionization is seen directly on top of the black hole's position. The emission of this light drops off with distance from the black hole. It follows a very predictable pattern of decline. Close to the black hole, nearly all of the hydrogen is ionized. Farther away, only a small fraction of it is ionized. At very large distances, the gas returns to being neutral atomic hydrogen. This gradient in the ionization maps out the radiation field that is coming from the black hole. Scientists can then measure the total luminosity that is needed, to produce the observed ionization. The calculation for this involves counting the ionized atom and knowing how long they will stay ionized before they recombine. If you multiply the ionization rate by the volume of the gas, you can get the total number of ionizing photons that are required. That number then reveals how much radiation the black hole is emitting. The collision zone black hole needs to produce a huge number of photons, about 10 to the power of 45 ionizing photons every second. This is what is needed to explain the observed emission. That is an incomprehensibly large number of photons. For comparison, our own sun produces about 10 to the power of 45 photons. It produces this many every second across all wavelengths. This black hole is producing that many ionizing photons alone. Each one of them is energetic enough to rip electrons off of atoms. That powerful radiation is coming from the accretion disk. As matter spirals into the black hole, gravitational energy is converted. It is converted into heat and also into radiation. The efficiency of this conversion process determines the luminosity. Black holes can convert about 10% of the infalling mass to energy. That is far more efficient than the process of nuclear fusion in stars. Fusion converts less than 1% of the mass to energy. Black hole accretion is the most efficient sustained energy generation process. The extended ionization that is seen proves something. It proves that the black hole has been actively feeding. It has been feeding for at least a few million years. The process of ionization does not propagate instantaneously. Radiation is known to travel at the speed of light. So, ionizing a region that is 10,000 light-years across, it will take 10,000 years at a minimum to do so. The observed ionization pattern requires continuous emission over a period of millions of years. This black hole is not just experiencing a brief feeding episode. It has been eating steadily for a very long time. The ionization signature also reveals the turbulence in the gas. The spectral lines from the gas show a broadening that is consistent with high-velocity dispersions. Dispersions of several hundred miles per second are seen. Different parts of the ionized cloud are moving at different velocities. This confirms the extreme turbulence that was inferred from other observations. The gas is not calm and quiescent in this region. It is in a state of violent and chaotic motion. The telescope also detected multiple ionization states. Multiple ionization states of different elements in the zone. Not just ionized hydrogen, but also ionized helium, and also ionized oxygen and ionized neon were seen. Each of these elements requires a different amount of energy to ionize. Hydrogen is ionized very easily by the radiation. Helium requires much more energetic photons to be ionized. Oxygen and neon require even higher energies to be ionized. Finding these elements in multiple ionization states indicates something. It indicates a hard radiation spectrum that is typical of black hole accretion. The team of researchers mapped the ionization across the entire collision zone. They created very detailed images that showed how it varies, how the ionization varies with the position in the cloud. The results of this confirmed that the ionization is strongest. It is strongest near the black hole and decreases with distance. No other source of radiation exists in the collision zone. No other source that is capable of producing this pattern. The ionization signature uniquely points to a supermassive black hole. This ionization mapping provided another key piece of evidence. The glowing gas is not just near the black hole, it is completely surrounding the black hole in all directions. The black hole sits embedded within an extended cloud of ionized gas. This geometry is exactly what the direct collapse theory predicts. A heavy seed black hole that is born from a gas cloud. It should remain embedded in that cloud for some time. It should be ionizing and accreting it simultaneously. The ionization signature converted the abstract concept of direct collapse. It converted it into concrete, observable predictions. Predictions that are a perfect match for the data. Theory and observation had finally aligned with each other. Science is known to progress by eliminating the wrong answers. It does so as much as by finding the right one. The Infinity Galaxy team spent a great deal of time. They spent time ruling out the alternative explanations. As much time as they spent supporting the direct collapse theory, every single competing theory needed careful consideration, and it needed to be refuted by the evidence. The process for this was very methodical and thorough. Alternative explanation 1 was that the black hole was ejected from one of the galaxy cores during the collision. This scenario is not completely implausible at first glance. Galaxy mergers are known to be able to eject black holes. They do so through what are called gravitational slingshot effects. When two massive objects interact with each other, they can throw each other around in a violent way. Perhaps one galaxy's central black hole got launched toward the central collision zone between them. The velocity test was able to kill this explanation. An ejected black hole would be racing through space. It would be moving at hundreds or thousands of miles per second. It would be moving relative to the surrounding gas. The measurements showed that the black hole was moving with the gas. It was not moving through it at a high speed. The velocity difference was less than 10 miles per second. That is not what an ejection scenario would look like. That is what an embedded object would look like. Alternative explanation 2 was a chance superposition. A third background galaxy was sitting behind the collision zone. It was perfectly aligned from our viewing angle on Earth. Its central black hole would then appear to be floating between the two galaxies. This would be due to simple projection effects. Astronomers call these chance superpositions, and they do occur. Multiple lines of evidence were able to eliminate this possibility. First, the velocity test was used again to check this. A background galaxy would have a completely different redshift, a redshift that would reflect its greater distance from us. The measurement showed that the black hole has the same redshift as the gas in the collision zone. It sits at the same distance from the Earth as the galaxies. It is physically in the collision zone, not behind it. Second, the ionization pattern was also used as evidence. A background black hole would not be able to ionize the collision zone gas. The ionization would be surrounding the background galaxy instead. The observed emission clearly associates with the collision zone gas. It does not associate with any kind of background galaxy. Third, a careful examination of the telescope's deep images. It revealed no third galaxy at that specific location. The team looked for stellar populations and galaxy structure. They looked for anything that would indicate a background galaxy. They found absolutely nothing in the data at all. If a galaxy had existed there, the telescope would have seen it. Alternative explanation 3 was that the gas contains numerous smaller black holes, not one single supermassive black hole in the center. Perhaps dozens of stellar mass black holes had formed from massive stars, and they were now orbiting within the central gas cloud. Their combined emission might be able to mimic a single supermassive black hole. The spectroscopic data was able to reject this scenario. Multiple small black holes would produce broadened but multi-peaked lines. This is because the different objects are moving at different velocities. The observed emission lines show single smooth profiles that are consistent with just one single object. The X-ray and radio emission are also point-like. They are coming from a single compact source of energy. They are not distributed across multiple different locations. Alternative explanation 4 was an intense starburst. The collision could have triggered an intense starburst in the zone. Maybe hundreds of massive stars had formed and then quickly evolved. They could have evolved into black holes which then merged. They would have merged into an intermediate mass black hole. The timeline for this simply does not work out. The collision happened billions of years ago, but stellar evolution takes time. And the black hole mergers also take a great deal of time. Building a million solar mass black hole from stellar mergers, it requires at least hundreds of millions of years. More importantly, the collision zone shows no evidence of past star formation. There are no supernova remnants or stellar populations of the right age. The turbulence in the gas had prevented star formation, which is the whole point of the direct collapse theory. Alternative explanation 5 was that the black hole formed somewhere else. It could have formed through normal stellar evolution. Then it could have migrated into the collision zone. This would happen through a process of dynamical interactions. Black holes are known to be able to wander through galaxies. Maybe this one had wandered into exactly the right spot. The probability argument is what defeats this scenario. Supermassive black holes that weigh millions of solar masses do not wander. They are simply too massive to do so effectively. They sit at the centers of galaxies held there by gravity. Getting one of them to migrate to an off-center location, this would require some extraordinary circumstances, and having it arrive precisely in the collision zone, with precisely the right velocity to match the gas. The coincidence of all of this is just too extreme. Each of the alternative explanations failed for specific reasons. The observations systematically eliminated every competing theory. What remained at the end was the process of direct collapse. It was not proven absolutely, because science does not deal in absolute proof. But it was supported by multiple independent lines of evidence. While all of the alternatives had fallen to observation and logic, the team of researchers did not stop there in their analysis. They considered even more exotic possibilities for the object. Maybe the black hole was a primordial one formed during the Big Bang, but primordial black holes that are this massive have never been detected, and they probably do not exist in our universe. Maybe it is actually a wormhole or a naked singularity, instead of being a normal black hole as we know them. But those hypothetical objects would behave identically to black holes. They would be identical for all observational purposes. So the distinction does not matter for this analysis. Every single alternative had been examined and then rejected. The evidence was all pointing in one single direction, the direction of the process of direct collapse. The early universe was a very different place than it is today. The conditions that existed back then have since disappeared. The direct collapse theory had originally predicted that heavy seeds would form. They would form primarily in a narrow window of cosmic time, between a redshift of 30 and a redshift of 15. This is roughly 100 to 300 million years after the Big Bang. This was the golden age for the process of direct collapse. Why was it then specifically that this happened? The first stars had formed, and they were providing Lyman-Werner radiation. This radiation was destroying the molecular hydrogen, but supernova explosions had not yet polluted most of space. They had not polluted it with a lot of heavy elements. The massive gas clouds therefore remained in a pristine state. The conditions had aligned perfectly, but only briefly. After a redshift of 15, the metal contamination became widespread. The window of opportunity for direct collapse had closed. The infinity galaxy sits at a redshift of 0.33. This is in terms of the cosmic time in our universe. That means that we are observing it as it was about 3.6 billion years ago. That is roughly 10 billion years after the supposed direct collapse window closed. The universe was already very old and metal enriched by then. Traditional theory says that direct collapse should not be possible. It should not be possible at such late times in cosmic history. This timing puzzle troubled the team of researchers initially. How could they possibly claim that this was a direct collapse if the infinity galaxy had formed billions of years too late? The answer to this lies in understanding that the two scenarios are different. The early universe scenario and the galaxy collision scenario. They both can produce direct collapse, but through different mechanisms. The early universe direct collapse relies on Lyman-Werner radiation. This radiation prevents the formation of molecular hydrogen. This then requires the presence of pristine gas with no metal contamination. The window for these conditions to exist was only brief. It existed only for a brief period in cosmic history. After the universe became metal-enriched, this pathway closed. The galaxy collision direct collapse relies on turbulence and pressure. These forces prevent the process of star formation. This does not require the presence of pristine gas. It can work even in metal-enriched environments. The extreme conditions of a violent head-on collision, they are able to override the normal physics of star formation. They do so through purely mechanical means in the gas. The turbulence will tear apart the molecular clouds. It will do so before they can form any new stars. The shock waves will compress the gas faster than it can cool. This means that direct collapse can occur at any cosmic epoch. It is not limited to just the very early universe. The physical mechanism is different, but the final result is the same. A heavy seed black hole is formed from a direct gas collapse. The infinity galaxy proves that this can happen in the modern universe. This realization greatly expands the significance of the discovery. Direct collapse is not just a relic process from the early universe. It is an ongoing phenomenon that can still happen. Galaxy collisions are known to occur throughout cosmic history. Many of these collisions might create the right conditions. The right conditions for the process of direct collapse. Heavy seeds might be forming constantly in the universe. They would be scattered throughout the cosmos wherever collisions occur. The team began to calculate how often these collisions happen. Major galaxy mergers occur roughly once per billion cubic light years. They happen once per billion years of cosmic time. Only a small fraction of those are head-on collisions, collisions with the right geometry and the right gas content. Maybe 1 in 100 of these mergers creates the right conditions. That suggests that direct collapse events are quite rare. Perhaps one event per 100 billion cubic light years per billion years. That sounds very rare, but the observable universe is vast. It contains about 400 billion cubic light years. Over all of cosmic history, direct collapse might have produced thousands of these heavy seed black holes in total. Not enough to account for all of the supermassive black holes, but a significant population of them nonetheless. Many of these collision-triggered direct collapse events, they might have occurred at high redshifts in the early universe. The galaxy collision rates were much higher back then. This is because the galaxies were much closer together. If you combine the early universe collisions with the traditional pathway, it suggests that direct collapse might be more common than anyone thought. The redshift window is not just a narrow period. It is any time and any place where the right conditions occur. That window of opportunity for direct collapse remains open today. The infinity galaxy is the proof that this is the case. Direct collapse is happening right now somewhere in the cosmos. We just have to find where these events are occurring. This changes the search strategy for these objects. Instead of only looking at the earliest and most distant galaxies, astronomers should now also examine the recent galaxy mergers. They should look for collisions that have produced intense turbulence. They should search for black holes in unusual locations. The next direct collapse discovery might be relatively nearby in terms of cosmic distances. Traditional direct collapse theory demands a gas purity that borders on the obsessive for it to work. 1 part in 100,000 of metal contamination can ruin it. The gas must be essentially identical to the primordial composition, the composition that emerged from the Big Bang itself, 75% hydrogen and 25% helium, and almost nothing else at all in the gas. No carbon, no oxygen, no nitrogen, and no other heavy elements. This purity requirement stems from how efficiently heavy elements cool gas. Carbon and oxygen are particularly devastating to the process. These elements have electronic transitions that radiate infrared light. They radiate it very efficiently, cooling the gas down. Even just trace amounts of carbon or oxygen are enough. They allow the gas to cool down rapidly by emitting infrared photons. Cool gas will then fragment into new stars. and the process of direct collapse will then fail. The early universe started out as pristine by its very definition. The Big Bang only produced hydrogen, helium, and a little bit of lithium. No heavier elements existed until the first stars had formed, the gas clouds in the first few 100 million years of cosmic history. They were naturally free of any of these metals. They met the purity requirement for direct collapse automatically. But the stars are what change everything in the universe. Massive stars are able to forge heavy elements through nuclear fusion. Carbon and oxygen are formed deep in their stellar cores. When those stars then explode as supernovae at the end of their lives, they scatter these heavy elements all across space. Each new generation of stars will increase the cosmic metallicity. The universe will become progressively polluted with these metals. The pristine gas will become increasingly rare over time. The Infinity Galaxy's collision zone gas is not pristine. Spectroscopic measurements have revealed its metal abundances. They are around 10 to 30% of the solar metallicity. That is vastly above the traditional direct collapse threshold. This gas contains thousands of times too much carbon and oxygen. By conventional theory, it should have cooled rapidly. It should have cooled rapidly and then formed new stars. The process of direct collapse should have been impossible. Yet a 1 million solar mass black hole sits embedded in this gas. Something must have allowed for the direct collapse to occur. It must have occurred despite the metal contamination. The answer to this puzzle is the turbulence and the compression. These mechanical processes can override the chemical cooling. When a gas is compressed rapidly through powerful shock waves, the heating of the gas will occur much faster than the radiative cooling. Even the efficient metal line cooling cannot keep up. The gas will stay hot because the energy is being pumped in. It is being pumped in faster than it can radiate away. Think of trying to cool a pot of water by turning on a fan. While someone is continuously adding more heat to the pot, eventually the heating process will win the battle. The turbulence is able to prevent fragmentation through a different mechanism. Even if the local regions of the gas do cool down slightly, the turbulent flows will tear them apart before they can collapse. The gas never stays coherent long enough to form any stars. Fragmentation requires thousands to millions of years of relatively calm collapse. The turbulence is able to disrupt this entire process. The collision also compressed the gas so rapidly that star formation did not have time to proceed. It did not have time to proceed through its normal stages, from the initial shock wave to the black hole formation. This probably took less than 10 million years in total. Star formation takes tens to hundreds of millions of years. It takes this long to convert a significant fraction of gas into stars. The black hole had formed before the star formation could consume the gas. This discovery fundamentally changes the direct collapse theory. Pristine gas is not required if other mechanisms can prevent star formation. Turbulent, rapidly compressed, and metal-enriched gas can undergo direct collapse. The chemistry of the gas matters much less than the dynamics. This opens up a whole new range of possibilities for this process. Many environments in the universe feature intense turbulence, and they feature a rapid compression of the gas. Galaxy collisions obviously qualify for this category, but also galaxy cluster mergers where multiple galaxies crash together, and also tidal disruption events where gas streams are torn from galaxies, and also the cores of massive starbursting galaxies, where supernova-driven winds can create a great deal of turbulence. Each of these environments might occasionally produce the right conditions that are suitable for direct collapse. The parameter space for this process expands dramatically. It expands when you remove the pristine gas requirement. Direct collapse is transformed from a rare early universe phenomenon. It is transformed into a potentially common process, a process that is operating throughout all of cosmic history. The team of researchers published these findings with careful caveats. They could not prove definitively that this was a direct collapse, but they demonstrated that metal-enriched gas can satisfy the conditions. It can satisfy them if the turbulence is sufficiently extreme. This theoretical framework then predicts observable signatures, signatures that are a perfect match for the infinity galaxy data. The pristine gas requirement was always the most challenging aspect. The most challenging aspect of the early universe direct collapse theory. Finding metal-free gas clouds that are bathed in Lyman-Werner radiation, but that are also shielded from the supernova ejecta. This seemed to be an almost impossible thing to find. The revised theory, which requires only extreme turbulence. It is far less restrictive in its requirements. Nature can achieve extreme turbulence through galaxy collisions. It can do so much more easily than it can maintain pristine gas clouds. The infinity galaxy represents something that is unprecedented, a test case for the process of direct collapse in the modern universe, a natural laboratory for studying processes that they thought had only occurred during the cosmic dawn. The collision had created conditions that should not exist billions of years after the Big Bang. It is the exception that proves the rule of the universe, while it is also simultaneously rewriting that very rule. Modern galaxies are known to live in a metal-enriched cosmos. Billions of generations of stars have lived and died. Supernovae have scattered their heavy elements throughout intergalactic space. The average metallicity of the gas between the galaxies now, it reaches 10 to 30% of the solar values. Inside of the galaxies, the metallicity can exceed the solar values. Finding any metal-free gas anywhere in the modern universe, this seems to be a completely impossible task to achieve. Modern galaxies also exist in relatively evolved states. Most of them have already experienced multiple mergers. Their structures reflect billions of years of cosmic evolution. They have already converted most of their gas into stars. The massive gas reservoirs like those in the early universe are rare. The fuel for forming anything massive is now depleted. The modern black holes already exist at the centers of galaxies. Almost every major galaxy is known to host a supermassive black hole, a black hole that had formed billions of years ago. Those black holes had grown through accretion and mergers. They have now reached equilibrium sizes that are related to their hosts. The era of rapid black hole formation is long past. Given these conditions, direct collapse should not happen. It should not happen in the modern universe at all. All of the necessary prerequisites for it are absent. The metal contamination has poisoned the gas for this. The massive gas reservoirs have been depleted over time. The black holes already exist where they are going to exist. The window of opportunity for this closed long ago. The infinity galaxy violates all of these expectations. The head-on collision between two gas-rich spiral galaxies, it had recreated the early universe conditions through mechanical means. The collision had compressed billions of solar masses of gas. It had compressed it into a very small volume of space. The turbulence from the shock waves had prevented star formation. Despite the metal enrichment, the timescale of the collision, it was shorter than the star formation timescale. This makes the infinity galaxy a modern exception, an event that should not have produced a direct collapse, but it apparently did so against all of the odds. The discovery is forcing scientists to reconsider the processes that can trigger the formation of heavy seeds. It is not just about the gas chemistry and the radiation fields. It is also about the dynamics, the timescales, and the violent events. Other modern exceptions might also exist out there. The team began to search the archival data for similar collisions. They looked for galaxy mergers with bright ionized gas bridges. They searched for X-ray sources in unusual locations. They also examined the velocity fields in the merging systems. If the infinity galaxy can produce a direct collapse, then other similar collisions might be able to do so too. Several candidate systems for this have now emerged. One of them shows a bridge of ionized gas between merging galaxies. It has a suspicious X-ray source in the middle. Another one displays extreme turbulence in its collision zone. A third one features asymmetric ring structures that suggest a very high energy impact. None of them are as clear-cut as the Infinity Galaxy, but they certainly deserve some follow-up observations. If direct collapse is occurring in multiple modern collisions, it would suggest that the process is more common than was thought. Every major head-on collision between gas-rich galaxies, it might have a chance of producing a heavy seed. The probability might be low, perhaps 10% or less, but it is definitely a non-zero probability. If you extrapolate this across all of cosmic history, this mechanism might have produced thousands of heavy seed black holes. Most of them would have formed during the earlier epochs, when the galaxy collision rates were much higher and the gas fractions in the galaxies were much larger, but some of them could still be forming even today. The modern exceptions also help to explain an observational puzzle. Astronomers are finding more intermediate mass black holes than theories predict. Black holes that weigh 10,000 to 1 million solar masses. They exist in surprisingly large numbers in the universe. Traditional theory struggles to explain their existence. They are too massive to have come from stellar evolution, and they are too small to be ancient galaxy core black holes. They do not fit neatly into either of the two categories. Direct collapse in galaxy collisions might be creating them. A heavy seed could form that weighs 1 million solar masses. It might never grow much larger because the gas supply depletes. It would then remain stranded at an intermediate mass. These objects would be scattered throughout the large galaxies, and also throughout the galaxy clusters where collisions occurred. The Infinity Galaxy might not be so exceptional after all. It might be representative of an entire population of these events. Collision-triggered direct collapse events that we have missed. We just have not recognized them yet because we were not looking. We were not looking in the right places with the right tools. Quasars are the brightest sustained beacons in the universe. They are able to outshine entire galaxies with their light. Some of them can emit more light than 1 trillion suns combined, and they are also very compact, concentrated into small regions that are smaller than our own solar system. These objects bewildered the astronomers who first discovered them. They were first found in the 1960s with radio telescopes. Only later did the scientists realize what quasars are. They are supermassive black holes that are feeding voraciously. The light that we see from them comes from their accretion disks. As matter spirals into the black hole at nearly the speed of light, friction in the disk will convert the gravitational energy to radiation. This process is extremely efficient at producing energy. About 10% of the infalling mass gets converted to energy. You can compare that to the process of nuclear fusion in stars. Fusion converts less than 1% of the mass to energy. Black hole accretion is the most efficient sustained energy generation process. To power a bright quasar requires a supermassive black hole, a black hole that weighs at least 100 million solar masses. Bigger black holes are able to produce brighter quasars. The most luminous quasars are known to host very massive black holes. Black holes that weigh billions of times the mass of our Sunday. These cosmic monsters are able to dominate the energy output. They dominate the energy output of their entire host galaxies. Quasars were very common in the early universe. The James Webb Space Telescope is finding them at high redshifts of 6, 7, and even approaching a redshift of 10. These ancient quasars existed when the universe was less than 1 billion years old. Some of them blazed to life just 500 million years after the Big Bang. This creates the supermassive black hole formation paradox, a paradox that the direct collapse theory is attempting to solve. To power a quasar with a billion solar mass black hole at a redshift of 7 requires that black hole to form, and to grow to that size extremely quickly, starting from a 10 solar mass stellar remnant and growing at the Eddington limit. This produces a black hole that is far too small. The timeline for this simply does not work out at all, but starting from a 1 million solar mass heavy seed, this changes everything about the growth process. That 1,000-fold head start in mass compresses the required growth time. It compresses it from being impossible to being barely feasible, a heavy seed that is forming at a redshift of 20. It has enough time to grow to billions of solar masses. It can do so by a redshift of 7 if it feeds continuously. It must feed continuously at the Eddington limit. The Infinity Galaxy discovery strengthens the connection between direct collapse and the early quasars. If heavy seeds can form through galaxy collisions in the modern universe, they certainly could have formed during the early universe. The conditions back then were even more favorable for this. The collision rates were much higher, and the gas fractions were larger. The turbulence in the gas was also much more common. Every early galaxy merger might have risked producing a heavy seed. This is able to solve the quasar population problem. Theoretical calculations had predicted too few massive black holes, too few in the early universe to explain the observed quasar numbers, adding a population of heavy seeds from direct collapse. This increases the number of black hole formation sites. More seeds will then mean more potential quasars. The observational signatures of this also match up. The early quasars show an intense ionized gas emission. This emission is surrounding their central cores. The gas around them is very turbulent and also metal-enriched. The X-ray and radio emission indicates that they are actively feeding. These properties are a good resemblance to the Infinity Galaxy's collision zone. It is just scaled up to higher masses and luminosities. Some of the early quasars also show evidence of recent major mergers. Their host galaxies are displaying disturbed morphologies, and they are also displaying long tidal features. This aligns with the collision-triggered direct collapse scenario, the same violent merger that built the galaxy. It might have also birthed the black hole that is powering its quasar. Astronomers are now searching for heavy seed candidates. They are searching for them in the early universe using the telescope's data. They are looking for compact X-ray sources that are associated with merging galaxies. They are searching for unusual emission line ratios that would indicate the presence of recently formed black holes. They are analyzing the velocity fields for signatures of direct collapse. Several promising candidates for this have already emerged. One X-ray source at a redshift of 8 sits between two merging proto-galaxies. Another one shows some spectroscopic features that are consistent with a newborn heavy seed black hole. A third one displays the turbulent ionization pattern, a pattern that is seen in the Infinity Galaxy system. None of these have been confirmed yet, but they are promising targets. They are promising targets for follow-up scientific study. If direct collapse commonly occurred in the early universe, it would explain not just the massive quasar black holes, but also the correlation between the black hole mass and the galaxy mass. Galaxies and their central black holes seem to evolve together. Their masses are known to be very tightly related. This correlation suggests that they formed or grew. They grew through a set of connected physical processes, direct collapse during galaxy formation and mergers. This naturally creates this kind of correlation. The same events that are building the galaxies through gas accretion, they are also triggering the black hole formation and growth. The galaxy and the black hole are growing in tandem. They are growing together because they are both fed by major mergers. The Infinity Galaxy is demonstrating this co-evolution in action. The quasar connection is able to transform the direct collapse theory. It transforms it from a theoretical curiosity into a crucial component of cosmic structure formation. It is not just about explaining a few weird black holes. It is about understanding how galaxies and black holes grow, how they grow together across all of cosmic history. The Infinity Galaxy is forcing us to rethink everything. Everything that we thought we knew about black hole formation, the rules that we wrote based on the nearby galaxies, and based on our computer simulations, do not capture the full picture. Nature has found some shortcuts that we did not anticipate, pathways that we did not include in our theoretical models. The universe is much more creative than our own imaginations. For many decades, astrophysics had taught a simple story: black holes will form when the massive stars die. The small black holes will then grow slowly through the process of accretion. Mergers will then combine the black holes into larger ones. Over billions of years, this process builds the supermassive black holes, the black holes that we see at the centers of the galaxies. It is a gradual, predictable, and also a linear process. This story made a great deal of logical sense to us. The observations all seemed to fit into this simple picture, until they did not fit into it any longer. The James Webb Space Telescope keeps finding black holes that should not exist in the early universe. They are too massive, they are too early, and they are too bright. The simple story of their formation completely fails. Either we are missing something fundamental about their growth rates, or the black holes have an additional formation pathway, a pathway that we did not know about before now. Direct collapse is now representing that second pathway. The discovery that direct collapse can occur in metal-enriched gas. It can occur through a process of collision-triggered turbulence. This completely rewrites all of the rules of the game. Direct collapse is not limited to the early universe, and it is not restricted to the pristine primordial gas. It can happen wherever sufficiently violent conditions arise. Galaxy collisions throughout all of cosmic history might produce heavy seeds. This process is therefore an ongoing one in our universe. This changes our understanding of the demographics of black holes. Instead of one population with just one formation pathway, there might be two different populations with distinct origins. The light seeds from stellar death will evolve into intermediate mass black holes, and they will eventually contribute to the supermassive black holes through mergers. The heavy seeds from the direct collapse will start out massive, and they will be able to grow much more rapidly. Both of these populations of black holes could coexist. They would be mixing through the process of galaxy mergers. Observationally, this predicts that we should find black holes. We should find them in some unusual locations in the universe, not just at the centers of galaxies where they are concentrated, but also scattered throughout the halos of the galaxies and in the space between the colliding galaxies. These would be wandering black holes that had formed during ancient collisions, and they had never settled into any stable positions. The Infinity Galaxy might be the first of many such discoveries. The rules will also change for the process of galaxy evolution. Black holes do not just passively sit at the centers of galaxies. They can influence the star formation through their radiation and jets. A heavy seed that is forming in a collision zone can suppress star formation. It can do so across thousands of light years of space. This feedback will then affect how efficiently the colliding galaxies, how efficiently they can convert their gas into new stars. The presence or absence of the direct collapse might determine something. It might determine whether the mergers will trigger starbursts or quench star formation. The rules will also change for gravitational wave astronomy. Colliding supermassive black holes will emit gravitational waves, waves that are detectable across all of cosmic distances. Future space-based gravitational wave observatories will map these. They will map the black hole mergers throughout the universe. If the direct collapse process is a common one, many of the detected mergers will involve these heavy seeds. The mass distribution of the merging black holes will reflect this. It will reflect two different formation pathways for them. This will provide a way to test the direct collapse theory. It will test it through gravitational wave observations. The rules will also change for the field of cosmology. Black hole formation is known to affect galaxy formation, And galaxy formation is known to affect cosmic structure formation. Direct collapse will alter the timeline of how structures grow, how they grow in our expanding universe over time. Computer simulations of cosmic evolution will need to be updated. They will need to include the collision-triggered direct collapse. They must do so in order to match the new observations. The parameter space of our cosmological models will expand. The rules will even change for planetary science in a surprising way. Black holes can regulate the galaxy-scale star formation, and star formation will determine the planet formation opportunities. The existence of any habitable planets might depend partly on this. It might depend on the black hole formation history. More heavy seeds means more feedback that is suppressing star formation. It will suppress it in some regions while triggering it in others. The distribution of any life-bearing worlds could be influenced by this, influenced by processes that are operating on million light-year scales. But we are still at the very beginning of understanding these new rules. The infinity galaxy is just one single data point. It is one single example and one single observation. Science will require multiple independent confirmations. It requires them before it will accept new ideas fully. The team of researchers published their findings as a candidate for a direct collapse black hole, not a definitive detection. The follow-up observations of this object are continuing. The telescope will observe the infinity galaxy again. It will do so with different instruments to measure additional properties. The Atacama Large Millimeter Array will map the cold molecular gas. It will see if any remains in the central collision zone. Future X-ray missions will study the black hole's feeding patterns. They will study them over long periods of time. Each of these new observations will either strengthen or weaken the theory. It will strengthen or weaken the direct collapse interpretation. Other teams of astronomers are now searching for similar systems. They are examining galaxy merger simulations to predict which collisions should be able to produce direct collapse. They are developing new observation strategies to identify heavy seed candidates. The hunt is now on for the second, third, and fourth examples. The fourth examples of collision-triggered direct collapse. If the infinity galaxy stands alone as a unique accident, direct collapse will remain an interesting possibility, but it will not be a major factor in cosmic history. If more examples of this phenomenon emerge over time, it will become a fundamental process that requires inclusion. It will need to be included in every model of black hole and galaxy evolution. The next few years of observations will determine which scenario is correct, but regardless of how common direct collapse proves to be, the infinity galaxy has already rewritten the rules. It has demonstrated that black holes can form in places, and they can form in ways that we did not expect. It has shown that violent collisions can recreate the early universe. It has recreated the conditions that existed back then. It has proved that nature still has some surprises waiting for us, surprises that are waiting in the archived telescope data. The universe has just taught us a lesson in humility. We thought that we understood black hole formation. We thought that all of the rules were finally settled. We were completely and utterly wrong about that. The rules are still being written in front of our eyes, and nature is the one that is holding the pen.